Welcome to another coding session. I'm Marcel. I'm creating a programming language, and today we're going to look at memory layouts. And the language is called Plum. It's on GitHub. And yeah, in particular I want to look at how aggregates are layouted. And like, what are aggregates? Well, the language has these kind of types. These kind of types. There are primitive types like int and string. There's a never type, for example. Panic evaluates to that, and the never type basically indicates that this will never be constructed, so it can be assigned to anything. You're gonna have a switch where one branch evaluates to an int and another one to never, and they are compatible. There are structs with fields which have a name and a type. And there are enums with variants, and each variant can have multiple payloads. There are lambdas, and types can be recursive. So in this case, like recursive 3 would mean, this plum type, in this plum type tree that you have, please start 3 layers up above this node. Yeah. So that they are used to represent like infinite recursive types. Right, and yeah, structs and enums, they both get converted into these aggregate expressions. These expressions have a fixed memory layout, and for structs, that will just be the fields of the struct with some padding in between. And for enums, those will be, depending on the value, actually different things. But basically the payload followed by a tag that indicates which enum this is. The tag is just a byte. And yeah, cool. So basically the question is, how can we lay out these aggregates more efficiently? And the way that layouting is done currently is that we build up these fields for structs. Those will be the actual struct fields. But just the memory layout of those, so a size and an alignment. And for enums, those would be the payload fields. And we call layout aggregate for each of the payload fields to get back this aggregate layout. And yeah, and then we put the enum tag always after that. The aggregate layout that we return also has a size and an alignment. And it has aggregate parts, which either reference one of these fields that we were passed, or it represents padding. And we need padding so that the fields are aligned. So, for example, one struct containing a byte and an int would probably, not probably, we can actually look at that. No, we don't have bytes. Well. You know what, let's still look at that. So I'm going to get into the main Plum file, which is here. And I'm not going to do anything except just manually lay out an interesting number of fields. So this layout aggregate accepts a slice of memory layout. So this is how you create a slice, and then we call layout aggregate. Yeah, and inside of that are several memory layouts with a size and an alignment. So here we have a byte, where the size is 1 byte. Unsurprisingly, and the alignment is 1, which means it can be stored anywhere at any address. And we have an int, which in Plum has 8 bytes, so it's a 64-bit integer. And the alignment is also 8, which means that it can only be saved at addresses that are a multiple of 8, because reading and writing from these kind of addresses is more efficient, and you can like read and write 8 bytes at once. So we want to layout them, and that should return an aggregate layout. think I'm just going to debug print that. Yeah. Yeah, let me get a terminal up and running. Okay. Okay, so we have an aggregate layout, makes sense. Size 16, alignment 8. The parts of that are first the field number 0, aka the byte, followed by 7 bytes of padding, followed by the field number 1, aka the int. Amazing. Yeah, and field, the byte field is at offset 0, the int is at offset 8, which is divisible by 8, so the alignment is respected. Now, of course, this is not the most efficient way to lay out these fields. You know, if we have, we could switch them around, basically, like this. And then we wouldn't need any padding. Yeah. Now we have an aggregate layout where the size is 9 and the alignment is 8. And yeah, first we store the int and then the byte right after that. And that's okay in this case. Because the byte can be stored anywhere, but here we had to add padding to align this field. Okay, yeah. This is a similar behavior to like how C compilers work. They have the exact same memory layouting of structs, which means that if you reorder struct fields, the struct may get more efficient and it may waste more memory or be more compact. And that's not something I want to have. I want this to be smart about reordering the fields. Similar to how the Rust compiler works, by the way. So how can we do that? Yeah, let me maybe brainstorm on my iPad and then okay. So basically we have our fields, which would be an int, aka 8 bytes, and a byte, which is 1 byte. And we want to put them next to each other in a struct. Yeah, they should be aligned differently. So the let's say alignment is, let's say this is, this is somewhere in memory, and these are the kind of addresses that are divisible by 8. Yeah. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So the int has to start at one of these boundaries here. Yeah, let me maybe remove that here. So in this case, we would like to choose this layout. Yeah. Boom. Put them together like this. I do think that figuring this out is quite complicated if you have many fields. Yeah, I mean the alignment can realistically only be 1, 2, 4, or 8. But still, like, I imagine having, I don't know, these fields, like, no. one field with size 2 and alignment 2, another field with size 1 and alignment 1, and maybe one with size 3 alignment 1, and yeah, maybe let's also say one with size 3 and alignment 2. There are a few ways you could do that. I think that putting this first is always a good idea, because now you're at alignment 2. You know, for example, it's nice that the one and this one, they sum up to something with alignment 2. Maybe, you know, intuitively I can kind of lay out these fields, but we need an algorithm to do that reliably. And maybe we can, let's maybe write down some hypotheses. Like, I think, let's look at laying out the biggest fields first, and then increasing the smaller fields, maybe? Maybe that makes sense. Or like, okay, even more simple, just lay them out in order, but if there are some gaps in between them, just fill them. Which basically means that if you have, I don't know, a byte and another byte, and then a 4-byte thingy, and this is like, let's say they are declared in this order, and this 4-byte thing has an alignment of 4. You could, for example, lay out the first one, then say, okay, next there's a field with alignment 4, which means that we need to start here. But then this field, we'll insert that here. So basically, we will check if any of the existing gaps in between the fields, they are enough to host these other fields. But I'm not sure I like that, to be honest, because yeah, let's write down some requirements for this. For our layout algorithm. Basically, it should be efficient. Layout, aka the layout should be as small as possible while still respecting the alignment requirements of fields. Then I think you should never be able to, you should never be required to think about the ordering of struct fields. Which means that regardless of the order that you declare your fields in, the struct should not get more or less efficient based on that. So field order shouldn't matter. Okay. Oh, somewhat of a meta idea is that the algorithm itself should be simple, because we want to interoperate with other languages at some point, I think. And that means that, you know, having this really complicated layout algorithm and having to explain that is kind of and having to re-implement that and re-understand that in other languages is kind of weird. So this should be simple and maybe predictable. Predictable, well, maybe, but definitely simple. Okay, so yeah, just going through the fields doesn't work. But maybe we can first sort the fields by their size or by their alignment, and then put them next to each other. Maybe that works. So let's try that. Let's say it's probably not optimal, I think. Let's say we sort by alignment. So we have this field, alignment 2, this other field, alignment 2, and then we also have a couple of fields with alignment 1. Or let's say only one field, with a size of 3 and alignment 1. So, layouting these would mean we would take the first field. Yeah, alignment 2 means alignment 2 fields need to start somewhere here. So the second field starts here. We need to add 1 byte of padding. Yeah, and the other, like the 1 field, we can't even fit that in there. So we put that afterwards, after in here. And that's not really optimal, I think. But at least that's a very simple algorithm. It doesn't have to be optimal, you know. I am fine with choosing something that's reasonably efficient. What about we order those fields by first by size and then by alignment? Maybe that works. So then we would take the field with alignment 2 and then maybe the field with alignment 1 afterwards, and then the final field with alignment 2. That is pretty cool. That is super cool. You know, let's just do that. I think that's that's not optimal. There were definitely cases where, yeah, I mean it's probably difficult coming up with one. Something where we sort by size and it's not optimal. Let's say we have something like this with alignment 2 maybe. Yeah, and then another field with alignment 4. Like here we would put the 2 first because it's more, you know, it's bigger. But then to respect the alignment of 4, the 4 field has to go here. Ooh. So we have 3 bytes of padding in between them. Whereas if we lay them out the other way, you know, first the one with alignment 4, then the one with alignment 2 is much more efficient. It's difficult. To be honest, I'm not totally sure what to choose here. I think in the Martinaise compiler I actually tried out like many different layouts and just, you know, with some limit, just try out all permutations of field orderings and see what the smallest one is. And that worked reasonably fast because of the limit, you know. But yeah, I don't know if that's like, that's not super elegant. And you can imagine even if you don't explicitly create fields with structs with lots of fields, just having some closure maybe that captures a lot of variables means that you create an aggregate in the background. So it shouldn't take, the memory layouting shouldn't take long for these kinds of scenarios. I think I'm gonna go with okay, why do these fail in some scenarios? This one up here fails because, well, there can exist fields with a very low alignment requirement, but with a huge size. Oh, that's the good case in here. I see. And here we laid them out according to alignment. Yeah. And that breaks if there are fields with small size, small alignment, but a big size, and they don't fit in these gaps that resulted from the fields with a bigger alignment requirement. Whereas in the other case here, this fails for, well, I think for fields with if the alignment requirement is same thing basically. If the alignment requirement is small and the field is large, then things get difficult. Like that's just a general property. If you have fields with alignment requirements of 8 or something and the size is really big, and then you have some other fields with alignment requirement of 1, like single bytes, and a small size, like you can put them in the gaps somewhere. That's no problem. The problem is if you have these small fields which are quite huge but have a small alignment requirement, then things get difficult. Yeah, I don't quite know how to deal with this. I mean, it can only improve on the status quo anyways, and the gaps cannot be super big, like they are limited by the alignment of your fields. The biggest alignment basically dictates an upper bound estimate of how big those paddings can be. So I think I'm gonna go with the size one actually. Sort them by size first, and then within those sizes by alignment, and then then see what happens. Okay, so oh yeah, for reference, let me maybe also show the memory layering of Martinaise. Yeah, here we have some layout. Yes. Yeah, here we basically just say calculate memory layout of, well, I don't even know what, but basically for structs we lay out all the fields, which is something we have already done for the aggregate. Then there's basically like an optimization, putting the fields where the size is a multiple of the alignment, putting them to the at the beginning of the struct, because they don't, it makes, you can do that greedily, that there is no disadvantage in putting them first. You just have less fields and you still have the same alignment. If you put them later on in the struct, they don't change the alignment. Like if you have some offset and then you put that field down there, then the offset is the offset plus that size, plus that size. Yes, so the alignment stays the same. Hang on. Oh yeah, that like multiple of the alignment here refers to the entire struct alignment, aka the alignment of the biggest field. Yeah, and then it makes no difference whether you're at offset 1 or at offset 9 in a struct with alignment 8, Yeah. Okay, so for all remaining fields, try all permutations, and find the one with the smallest overall size. Right, so that's like is this hacky? I don't know. Maybe. Yeah, we only try the first 1,000 permutations and then we just give up and choose the best one among those. Yeah. Okay, but I think we can work with that. Let's yeah, I should maybe like document the thought process behind that and the requirements as well. Always good to have these things in the source code. Now, is there like think there's like a general thing actually for the file. Yeah. If that means sacrificing on how simple things are, then I don't think that's the correct thing to do. But I can't even read what I wrote there. Yeah, size of data structures should be small. Just call it small. This is the priority. Like field order shouldn't matter, period. Like that's a given. Layouting should be simple. Yeah. These are our commands for choosing memory layouts. Order it in prior, order from most important to least important. Or let me put that down there. Maybe not. More and more requirements. Yeah, we need to lay out a lot of types. Responsive. Yeah. Good. Very nice. Yeah. So we have the fields, and hang on, what do we do here? Oh yeah, we just take the index of the field, and then we take the item. Then the size before padding. Okay. So I think we should maybe sort the fields. Yeah, I think so. Sort the fields first by primarily by size, secondarily by line, and this should be stable. So if you have a struct with an x and y and both are ints, like just a point struct, then we should keep the order of x and y, and the memory should not be like y and x. That would be cursed. Okay, yeah, I don't know if I have a stable sort in standard lib. Well, let me maybe look at standard lib mem. If slices are defined in here. Oh, look at that sort function. Amazing. Yeah. Quicksort. Is quicksort stable? I don't think so. I'm not sure. Stable sort. Sure. Yeah. You have to basically the same. Then we want to retain the order. That's the thing. Yeah. Yeah, unstable. Yeah, quicksort is unstable. They can be made stable. Oh, I see. Yeah. Yeah, that is true, because we can just primarily sort by the original sorting criteria, and secondarily by the index, the original index in the list. That's genius. Okay. So yeah, I think this just uses, yeah, this less than, and less than is implemented using, the less than function uses this operator, and you have to implement that for types. I'm not sure I want to implement this for memory layouts. Plus, we also want indices to work correctly. So I think I'm actually going to add a new like helper type, basically. Like field memory layout, or aggregate field memory layout, I don't know, something like that. Similarly, as size has alignment, but also has the field index. And yeah, you can basically let's just map the fields first. So yeah, fields is already taken by this. Mapped fields, I don't know. Naming is difficult. I'm gonna hopefully choose a better name later on. Yeah, let's just get them all and then just put them into the mapped fields. So this would be I see. Yeah, something like this. Okay. Then we'll implement this operator for field memory layouts. And what that's gonna do is, well, compare the size first. So a dot size compare to b dot size. Yeah, if that is equal, or if that is not equal, yeah, that should be, yeah, let's say this is equal, or if it's not equal, then we just return that. And it's going to return an ordering. Same with the alignment, and finally the index, and this should be unreachable, because you shouldn't ever, like, you shouldn't ever compare a field with itself, right? Yeah. And all fields have different indices, so yeah, one of these is going to trigger. I mean, yeah, let's simplify this. Okay, yeah, I think then we can just do fields.sort, I guess. Hang on, let me see, yeah, and slice, beautiful. Stable sort the fields primarily by size, secondary by alignment. Now, you know, I'm just gonna go sort the fields by index, making the sort stable. Amazing. That's pretty cool. So now we have fields, and we want to map them in memory. You know what, let's just run this and see if this already changes things. Oh, well, that hurts. Oh yeah, because we have the smaller one first. Right, primarily by decreasing the size, sort the fields. Okay, so we actually want to flip that. Is there a flip method on ordering? I hope so. Ion is equal or we can just check like a dot size equals b dot size or we return something. Oh, that's amazing. That is pretty crazy. You know, if the sizes are not, yeah, I think maybe an if is even more readable here. If a dot size is not equal to b dot size, then a dot size is not equal to b dot size, then we return the flipped size because we, you know, those should be decreasing. And if a dot alignment is not b dot alignment, then we return the flipped alignment. Otherwise, we return the comparison of the indices. Okay, that's amazing. So let's see what happens now. Efficient layout. First the int, then this other field. But now if we switch them around, that should still be the same layout. Amazing. Okay. So yeah, memory layouts are now independent of the original order. That is amazing. Okay, so now let's try some of these layouts that I had in here. Test 1 is this. Test 2 will be a field with size 3, alignment 2, size 2, alignment 2, and size 3, alignment 1. Oh, no padding. That is cool. And yeah, reordering fields doesn't change anything, so that's pretty amazing. Okay, so now the third test, and that should be less optimal. Memory layout is something with size 5, alignment 2, and size 4, alignment 4. Yeah, 3 bytes of padding. Yeah, that's not optimal, but that's fine. You know, let's go for something realistic, like a struct containing something with size number 3, alignment 2, then a byte size 1, alignment 1, and then something bigger like size 5, alignment 4. This could be like a maybe even this. Yeah, this could be like a maybe int or something. Int plus tag at the end. Doesn't look too bad, I think. So the order is exactly the order that we specified them in. That's interesting. Hang on, 0, 1, and 2. That's surprising. Because I would have thought that we first sort them by the size. Right? Oh, hang on. Oh no. I think in here we just don't choose the correct index. Yeah, here we just go over these, but we shouldn't do that. We should just directly choose the field. Yeah, the index is inside of the field. That we don't want to enumerate these again. We did that up here before we sorted them. So now we get the index from, that they contain as a payload in here. Yeah, okay. So field number 2, then 1 byte of padding, field number 0, and field number 1. Yeah, that is fine, but we have field number 2, aka the maybe thing, the big one. Then we have 1 byte of padding, and then a field with alignment of 2. But then field number 1, which is a single byte. Yeah, this is a single byte. I think this should just slot in between those fields. So, how do we do that? I think rather than building up these parts directly, including parts like padding, for example, we instead want to only store fields to offsets, and for the padding maybe insert these like store separate, basically a list of paddings that are available maybe with offset and size and alignment. Well, you can get that from the offset, but then basically when you encounter a new field in here, you first go through this list of paddings that exist and see if that fits somewhere in there. I think that's more sane. So rather than building the parts directly, I don't even know. I guess we store size, like I guess the current size, and then also field to offset. I'm just gonna go ahead and see where things go. Okay, so we have fields. Before we do anything, we also keep around like paddings, which will be a list of paddings, aka let's say tuples for now, that contain an offset and a size. Yeah. And then here we basically do this, like check if the field fits in padding. And then, like, that's to do. Doesn't fit in the padding. Add it to the end. Amazing. Yeah, size before padding equals size. Yeah, we don't have parts in here. But we do need to push something to the paddings. Mm-hmm. Cool. Yeah. Yeah, I'm gonna refactor this later on to something a bit more readable. And in here we just go over the paddings. If it can fit somewhere in that padding. It doesn't have to be at the start. Oh man. Oh, this feels horrible, you know, keeping these lists and so on in sync. I'm just gonna do like a totally naive thing and just have a list of bytes, like a list of ints, I guess. Yeah, where each item in the list represents one byte in the final layout. Like each item in the list yeah. Okay, and then basically for field and fields, minus 1 means padding. First we see if it fits in some padding. So for I in 0 to bytes dot len minus field size. Let's do it next. Yeah. Yeah, we basically look at all possible offsets that we can store this field at. And first we just store that here at bytes dot if offset plus field of size is larger than bytes dot len, then break. We haven't found a field. Otherwise, we do stuff. We check if bytes dot subslice from the offset and field size, if all of those are minus ones. Is all padding, and is all padding is function on bytes. Slice of int is all minus 1. Yeah. Amazing. So we just check if this is all minus 1. If so, then we want to place the field there. Which means that, you know, for I in offset to size, we basically say bytes get dot set I to field dot index, something like this. Amazing. Yeah, this is like a very naive way to do that, but I think it's fine. Because structs just aren't that big, I think. Okay, so things is all minus 1, sure. Now I want to... Oh yeah, if we... Oh yeah, here we want to basically break out of the loop, but continue to the next field. And there was no way to do that elegantly, so... Wait, there is field equals... I think you can do this. Yeah, nice. And if we haven't placed the field, then we just add it at the end of the struct. Which means we're essentially going to do this. Yeah. Cool. Size is size.round up to multiple field alignment. I think there's like needed for multiple of, yeah. Oh. Yeah, something like this. And then in the end we can say field to offset. I mean, this might actually be useful. We might want to do that here as well. Yeah. Mm-hmm. Yeah, okay. That's pretty cool. Now we want to calculate the entire size and alignment, the parts and field to offsets and so on. Sure. And that's gonna be interesting. Yeah, maybe we don't need that here after all. Oh yeah. No. Well. These are some nice parallel structures. Nice. Yeah, and that's kind of difficult. What are we gonna do here? Now we basically want to go through the bytes. And, well, just calculate the parts, I think. The mapping, yeah. Then we want to consume other values that are the same, basically. So I have another loop in here. And then if this is the start of the field, basically. Yeah. Expected the name of the variable. I think here we just look at the field. Yeah. If value is -1, then we do parts dot push aggregate part dot padding of that length. So and minus the initial offset. Otherwise, we're gonna do parts dot push aggregate part dot field of that value, and field to offset. We're gonna put the field index, aka the value, to the initial offset. Amazing. Oh yeah, and afterwards we're going to offset equals end. Very cool. And finally, size and alignment. Yeah. I mean, that's basically just this, right? Nice. compiles amazing. Oh, this is super efficient. Like the, oh, nice. But we can even see the fields in here. First we have, oh, where's my mouse? Here we have 9 bytes of field number 2, which is like maybe of int or an enum containing an int maybe. Then we have field number 1, which is a single byte, and then field number 0, which was size 3, alignment 2. That is pretty amazing. And let's actually let's print the intermediate steps, because I think that's gonna be fun. Yeah, we'll just print the intermediate layouts. Damn. Okay, so initially we start with an empty thing, then we push the first field, which is going to be the biggest, and then we push the second biggest, and because that has an alignment of 2, we add 1 byte of padding before that. And then the next field is size 1, so it fits in here. So we actually just insert that. That is super nice. Okay, so we reorder fields, and like you can see here, you know, we ordered fields for everything to be super efficient. Oh, that is amazing. That is honestly amazing. Damn. Okay. Yeah, let's maybe push that to get amazing. And this is, by the way, more efficient than Rust, for example, because in Rust the size has to be a multiple of the alignment. So in this case, in Rust, the field would have a size of 16. And that compounds if you have nested values in Rust fields. So let's maybe open some Rust project. Oh. Well. Like just random project, but if you have a struct, oh yeah, with a field that is an option of usize, for example, oh, I see. Okay, so maybe put that in somewhere here. Yeah, and you can see that the size of this is 16. That is more surprising than I initially thought. I thought this would be 24, actually. Okay, so this has size 8. Hang on, if we only have one option. Still size 16. also weird. Yeah. Yeah, okay. I mean, in our case, we would just add, you know, 1 byte for each enum that we wrap around something. Which I think is a sane and predictable approach. It means that when you store multiple values of the same type in memory next to each other, you may need to add some padding, because you have to round up the size to a multiple of the alignment. But I think that's a saner concept. Okay. What else? Yeah, let's first push this maybe. So we have a foo. Hang on. Yeah, I already closed the Rust thing. I thought, like my initial, I thought there were some cases where Rust is like really inefficient with structs. Like, let's say you have some option usize. That's 16 bytes. And then if you have a byte in here, 24 bytes. I don't get it. Why is this? Or maybe if enums, probably there's some special handling for structs that are basically enums, you know, that only contain an enum. And if you have multiple enums that nest, then those tags kind of get condensed, maybe, like joined into some more efficient layouts. But still weird. Like that's super weird. Yeah, no. In our case, that would be 10 bytes, I think. Let's try that out. Let's remove this part. And in the test.plum file, which is here. Yeah, let me open another VS Code where we have syntax highlighting. Nice. So let's say, this looks pretty nice. So let's say we have a struct that is very similar, that has a maybe int and a byte. Oh, we don't have bytes, do we? Maybe we should add bytes. Let's just create such a struct, like foo equals and like foo of an int. And that's going to create a struct where a is sum, a and b is just a. And to make it not confusing, let's maybe use a different variable name for that. And it's going to be make foo of that a. And then we maybe return foo.b. True. This needs a return value. Return type. This returns food. Yeah. Okay, so casting this to that is not supported. Well, I guess we have something to to look at. Why does that not work? Yeah, let's maybe first commit the more efficient memory layout. No. Make memory layouting more efficient. And then let's look at this. So casting is not supported. Okay, so we can cast enums. Well, we can't cast structs. What? That should work. In fact, that should be easier than casting enums. How does this work? We do a builder.push. In our case, we don't even need to switch on anything. We just build a struct of some, switched values. And the way we do that is we map the individual fields, similar to how we mapped the individual payloads here. Right, how does that work? We take the payloads, which are these are types, two payloads, also types. And then we build a case where we have params, the original payloads. Okay. And then from payload IDs, two payload IDs. And then here we compile the cast function and stuff like that. Cast is case builder.push. And then we build a variant. Okay. So let's do something similar. We get the struct IDs, I think. So from fields IDs is a list of your good IDs, where we just go over the struct like this. Yeah. Oh, hang on. This is there's something from. There's like a type level thing. We want to go over the actual. Hang on. Param is a yogurt ID. What do we do with param down here? Oh, here we switch on the param. Okay, I think we want to get the member of the param. Yeah. So for each field, we want to get the members. So we want to push yogurt up. The member of our struct, so param, with the field name, or key, I think, in this case. Yeah. Well, like that. And then we have the from and to fields. Then we can, we should get the types as well, I think. No. This call doesn't work. Push yogurt up. Yogurt fun builder needs a yogurt expression, so this also needs a type, I think, which will be a field type. Oh, but hang on, this will be the from type. So from dot extend. You know, just to be safe, let's do it like this. Oh, like this. And this will be from. Oh, hang on. Oh, yeah, here we just unwrap. And we don't need to extend that explicitly here. Amazing. Yeah. Oh yeah, so the from is also a struct, we know that. Yeah, and then this is gonna be from dot field dot type, field dot value in this case. Yeah, and the two field IDs will be a list, okay. So far so good. Here we have the types matched up. I mean, sure, we don't need that. We just go over the from field IDs. And we get the from payload type. Let's merge these into one loop. So we have the from type, from field type, which is gonna be field.value. We have the to field type, which is gonna be struct.get field key. We have the name, which is the field key. Amazing. And then we build a yogurt ID, we access the member on the original parameter of that name that is supposed to be the from field type. And then instead of pushing, I mean, cast fields. Oh yeah, this is going to be a map from string to yogurt IDs. So here we put the yogurt ID under that name. That's amazing. So we get that field. Oh, hang on, but that's not cast. That's the original field. So we need to call the cast function. aka ourselves recursively. So there's going to be cast fields dot put name. Let's call it maybe original ID, and then cast ID is something. Yeah, and that's just the builder, I guess. Yeah, builder dot push a call of compile from field type to field type, and the argument is the original ID. And the type is the to field type. Amazing. Yeah. Nice. And then in here we can just build a struct. And that needs a map of fields. And I think we can just put the cast fields in here. Yo. Amazing. Oh, amazing. Oh yeah, yeah, the 2 in here should be, yeah, maybe let's do that in here after all. Like on demand when you navigate down into that. I guess. Okay. Let's just try that out, see what happens. Interesting. So we have some cast function. Oh yeah, we should see that up here, right? Casting an enum, casting a struct. First we call cast this enum to that of parameter 1. Oh, no, that doesn't exist, apparently. That's bad. Oh, because I think this should be builder.push. And that's it. I think that looks good. Okay, so we get... let's look at this one first. So we get field A, and we cast that field to this enum. Amazing. We get field B, which is an int, cast that. Sure. Then we build a struct containing the cast fields, and we return that. Okay, perfect. Honestly, this is perfect. And then in here we... Oh, damn. What's going on here? 7 lines of padding. Interesting. So we cast this some int and int to something. Oh yeah, that actually makes sense. We put this 2 in here, which is going to be this enum, which is... Oh. Yeah, like this is not the optimal memory layout. Ah, that is sad. That is really sad. Yeah. Okay, so I mean, you know, we cast this. This is gonna be 9-byte something. We cast the int, which is always 8 bytes, and then here we put the 9 bytes 7 byte of paddings to get to 16 bytes, and then the int aligned to 8 bytes. And I see how this makes, how that's the result of our memory layouting strategy. We're first putting the biggest field and then the smaller fields. 7 bytes of padding in between, that kind of sucks. That really sucks. And I don't know how to do that, how to deal with that more elegantly. Maybe we should, I don't know. You know what, let's maybe first push this, because again, this is something self-contained. Support casting structs. Okay. And then let's revisit the memory layout, because how do we order these fields? Maybe let's first put fields where the alignment basically we want to do what we did in the Martinaise compiler. Something like this, you know, fields where the size is a multiple of the alignment, of the entire struct alignment. They should be put at the beginning of the struct. How do we do that? Maybe we can sort those fields according to the alignment modulo 8. Sounds weird, but like, you know, in general, I'm happy with how the memory layouting like fills holes and inside the layout and so on. That part is good. But sorting these fields, I think let's just adjust these and play around with that. So yeah, obviously we don't want to store the bigger fields first, because in the struct with an enum and an int, we don't want to store the enum first. And then because there's a tag, we have to add 7 bytes of padding before the next int. Now we want to sort the int first, and then the enum, so that the entire struct also just has like 17 bytes, an int, and 1 byte for the tag. No padding required. So maybe we should, yeah, let's sort these according to the alignment, I think. Like first alignment, modulo 8 being 0, then hang on, the size, according to the size modulo some global alignment. That seems so arbitrary, like super arbitrary. I mean, we want to sort, we do want to sort small things later on. In general, like small or we want to sort things with smaller alignment later on, because we can fit them, you know, in these gaps more easily. Yeah, I think let's do that first. Let's take alignment as the first criterion. First, lay out all fields with alignment 8. And within those, we can first lay out the small ones. I think we basically have 2 tiers, basically. Like, if maybe we want to go at this from 2 sides. Like, we look at the fields with the highest, just look at the fields with the highest alignment. How is there no, you know, that's maybe, this is supposed to be a solved problem, right? Like, there are probably some papers and stuff about how to do this efficiently. Like, I think I googled for that when I worked on Martinaise, but I'm not entirely sure. Like struct layouts, struct layout optimization, that sounds good. Okay, now let's just look at some papers and see what not aircraft stuff, okay. Practical structure layout optimization and advice, okay, so yes. Oh, okay. A practical implementation of the structure splitting. Not sure what that is. Structure peeling. No idea. Structure field reordering. Oh, and that field removal. Okay. Oh, legality. I mean, yeah, that's like for, you know, for C and C++, where some of these things are really in the standard. You know, if you declare a struct with a certain, like, I'm assuming this is for like very low-level languages where you have access to the memory layouts, and where that is surfaced in the language itself. Interesting. I'm assuming this is not. Oh no. Yeah. Let me get this. Okay, here we are. Yeah. This seems old. From when is this? 2006. Yeah, that's maybe, like, this is interesting, you know, reading about these Oh, interesting. This is really interesting. Structure peeling. New variables or pointers are created. Right. Okay, so here we have, oh yeah, this is the original thing, where we have structs with field 0, 1, 2, 3, and another struct with field 0, 1, 2, 3. Oh, but field 0 and 2 are accessed very often, and field 1 and 3 basically never. So some of these are hot, some of them are cold. And they do this. They factor out these cold fields into separate memory, so that in this part of the memory is data that you actually need. And this data which you access basically never, you know. If you need that, you can still get to that. But it doesn't like clutter your cache, so things are more compact. I mean, we don't do that right here. I'm just interested in struct field reordering. Is there like field related work? We order structure fields for type-safe languages such as Java. That sounds interesting. 12. Okay, yeah, I mean, sure. Structure splitting, and okay, so 3 and 12. Mm-hmm. Yeah, okay, not as fitting to our use case. Oh, no, that sounds cursed. I mean, yeah, it's pretty cool, and I'm willing to do some things to make the compiler more performant, but if the complexity is like growing super fast, meh, I don't know. You know, memory layouting is something that is, I like the current API of that. It's like a small little bubble where you can experiment and do things more efficiently. Yeah, but I don't want to, like, you know, if you have multiple fields in a struct, then I don't want to interleave these fields because that makes, like, that basically is a leaky abstraction. That means that other code has to worry about that. Struct fields are not even in memory right next to each other, because yeah, it makes sense. I get that their performance I'm just not going to reach because of that, but I'm fine with that. Field reordering, you know, that's something quite contained, but you can still do a lot with that. Okay, so let's maybe look at some of these references that apparently talk more about field reordering. I think 3 and cache conscious structure definition. Interesting. And the other was number 12. Automated data member layout. Data member layout of heap objects to improve memory hierarchy performance. Memory hierarchy, that sounds like you know, putting cold fields somewhere else. That's not about the denseness of the fields, I think. But maybe. I mean, let's just look for this one. what else is there? Like structural design? Yeah, no, that's not for multi-threaded. Oh, because the multi-threaded is even more complicated, where you have memory. Yeah, if you access the same memory basically from multiple threads, that's super inefficient because the threads have to organize, like coordinate to give a consistent memory model. Yeah, no, that's not our use case. So yeah, not as nice. Not structural design. No, not at all. What we're doing. Okay, so let's look for these papers. Cache conscious structure definition. A program's cache performance can be improved by changing the organization and layout of its data. Yes. Yeah, I know. Mm-hmm. Okay, field reordering, at least. Yeah, let's maybe look at that. Reorder. Sure. Nah, I'm just gonna scroll through. Yeah, they explain caches, structure splitting. Oh, average size. That's also interesting. Sure. Table 2. Oh, down here. Most heap allocated Java objects are small. Okay, that's not super surprising. Okay, yeah, that's. I mean, that are already quite a big number of bytes. Field reordering. Yeah, okay. Okay. So they actually look at how fields are accessed and do stuff. And use that information to reorder fields, so. Yeah. We only want static analysis. Okay, so they have the structure, struct access database. Okay, they do some weight thingies. Okay, yeah, but it's really about doing this experimentally, and I'm looking for like field reordering is a nice term for that, I think. Field reordering, efficient, compact field reordering. Struct. I mean, yeah, you can do that. Yeah, I don't want this. Oh, I want something that's deterministic. Oh, this. Oh, it's a book. We order field. No, not really. Yes. Like a spatial locality is what I want to reduce. Oh, that's what I read. Oh yeah, that's exactly that one. Okay, what else was there? There was this... Like, I think at some point this is like the knapsack problem. Like, it's impossible to get an optimal... Oh, you know what? That's actually... Like, there are probably some heuristics for the knapsack problem, right? Yeah, let me maybe... no, it's not quite that. I mean, the brute force approach of just trying out different orders seems so wrong. In Rust, it's pretty simple actually, because of the limitation that the size is a multiple of the alignment. Yeah. Okay. Yeah, okay. So this makes things really easy. Really, really easy. And yeah, the representation for C is... yeah. No. Oh, what's transparent? Oh yeah. Okay. There must be languages with... That's like... Why has no other language this problem? I don't know, Haskell was also statically typed and has enums. Yeah, I guess. Memory layouts. Maybe. Yeah, they have alignment stuff. Ah, nice. How does that work? Memory, layouting, types. I don't know. Maybe. Memory footprints. This sounds interesting. Okay, so we have atomic types. with different sizes. Bool has size 0. What the hell? I'm not sure that's correct. Wait, but int has 3. Oh. No, I don't get it. Okay. Well, yeah, box types, yeah, they suck. Yeah, this. Exactly. For each constructor and each type in use. There's a space missing here. So hash make bool v will have a smaller footprint than the value of hash map my int list v. Yeah, okay. I think they don't really care about ordering, I assume. Because that sounds like they just use pointers all over the place. Even for bools and so on. And that actually makes sense for this. So they basically have 2 bool instances on the heap somewhere, probably. And they store them inline or something. So they don't actually store anything. Like the better char on an 8-bit integer occupies 2 words, aka 16 bytes. That's crazy. That's really crazy. Yeah, no. Okay, is there a language that... Hang on, rock is... We could look at that. I want a language that has enums and that cares about efficiency and memory layouting. Oh, but rock just uses LLVM. So let's maybe look at LLVM. That seems like state of the art. Okay, yeah, that I should have thought of that earlier. Oh, nice. High level structure. Okay. Data types, type system. Aggregate types. Oh, hell yeah. They can contain multiple member types. Oh, yes, arrays and structs are aggregate types. Amazing. So the array type, sequentially memory. Okay, sure. Array type, structure type. Haha. Load and store. Yeah, no, that's... Yeah. Does this do reordering? Okay, like whatever identified types are. Oh, types with an identifier. Oh, that's weird phrasing, but okay. Let's maybe look at structs. Get element pointer. Please don't tell me it has the offset. Type pointer and then which of the elements are indexed? Okay. Okay, I want to see how LLVM internally layouts aggregate types. Okay. LLVM aggregate types layouting. Nope. Nope. Maybe. That sounds interesting. Kind of everyone doing the same things. Yeah, okay. Field reordering. No, where's field reordering? It's always mentioned, but no one... Okay, so there's this. Field reordering. Can't start with that. Structure peeling, splitting, field reordering. Peeling, splitting. Reordering. Yeah, okay. Phase ordering problem. Just reordering the fields. Nope. Okay. Yeah, the documentation could probably be improved. Whatever changes you make in the generic part of the IR, you have to implement. This, maybe? You know what? LLVM source code. Let's look at the struct layouting and field reordering. Layout as layout, not the sections. struct layout maybe. 4.7. Maybe field reordering. Instruction reordering is something else entirely, so. Oh man. Oh. Interesting. Check for excessively padded struct. Detect structs with excessive padding, which can lead to wasted memory. Yeah. Yeah, this is not good. Oh, but it's just I don't even know where to look in here. LLVM docs. Or rather, docs readme. Yeah, hang on. Pack, maybe. I don't know. There should be a good way to do this. And it bothers me that Rust doesn't, I mean, a Rust struct with an option new size and a single byte is 24 bytes. That is crazy. Like it bothers me that they don't care about memory layouts. I would have imagined that they had something better than that. Can't be that I'm the only person who cares about it. Maybe it doesn't make a huge difference in the real world, I guess. Well, it's still strange. Super strange. Okay, maybe back to the drawing board. Okay, so I mean, the fields that you have to lay out, you can summarize the information you need. You can basically say, we only have alignments of 8, 4, 2, or 1, and we'll just track how many fields do we have that need an alignment of 8, 4, 2, or 1, and what is their size modulo 8. Yeah, because for example, if you have a field like this, you know, size, needs an alignment of 8, and the size modulo 8 is 0, you can always put that field at the front of the struct, greedily, because there is no, you know, if you're currently layouting a struct and you're at some offset, no other field will even, you will not inhibit how you can place other fields by going 8 bytes further, because you're still at the same offset regarding modulo 8. But you have one less field to worry about. So that would always be something you want to do. And similarly, if your struct doesn't have any fields with alignment of 8, then you only care about the alignment modulo 4. Oh, you know what, let's maybe start at the bottom. Let's look at the most simple, the most obvious ones. Like, let's only look at fields, only fields with alignment 1. That's trivial, because you can always just put all of them next to each other. There are no restrictions. Next, only fields with alignment 2. Now things get, hang on. Well, with alignment up to 2. So 1 and 2. And let's maybe build this table. You know, we have the size modulo stuff. Modulo 2, size modulo 2. Yeah, maybe let's put the most challenging one up front. Okay, so if you have a field of size 2, and a field that requires alignment 2, and the size modulo 2 is 0, then you can just place that field. Like, you can place these fields, there's no downside in placing them first. If you have fields with size 2, and you have another field with alignment 2, but the size is like 1 or 3 or 5 or something, if you compare that with a field of size 1 with the same size, that's also something you always want to do. So you want to, pair these if you can. Let's maybe do like, first you want to do this, next you want to do this, and only then place the 1 fields. Like, this is a strategy that always works. Yeah. Now only alignment up to 4. So 1, 2, and 4. And I think in here things get complicated. Like, size modulo 4 is something we have, and then we have fields with alignment 4, 2, and 1. And the size is 0, 1, 2, and 3. Again, you can just place these down. That's always good. Well, now things get difficult. If you have a field of size and that requires an alignment of 4, yeah, we can even have the no, I don't know, an alignment of 4, and the size modulo 4 is 2, like this field. You can pair that with one of these, and I think that's always optimal. Yeah, I don't know why though. Like, this is just based on intuition. That's probably not the best reasoning. Similarly, you can, you know, pair this with, oh no, you can't do that. And because this still has to be aligned to 2 bytes. Never mind. Plus, you know, choosing an optimal layout. Like, this is definitely not an easy algorithm, having these tables and like, what's the underlying principle that makes some of these like very obvious candidates? I think, let's say you're at some offset, say module 8, like 8 byte aligned. Yeah, I think you want to choose fields. Like, okay, if you have the option to choose a field, here's the next 8 bytes. If you have the option to choose a field that is 8 bytes in size, you want to do that. You really want to do that. If you have why? Because I think these are very common fields, common scenarios in the real world as well. You know, having these fields, like in our maybe case, that are aligned to 8 bytes. So I think okay, I think I have some strategy. I don't know how it works on real world data. Let's choose a field, alignment 8, and judge the field's quality based on how much padding you would need to reach another alignment of 8 bytes. So basically, if you have our maybe field, maybe of int, that is 9 bytes in size, this is a bad field to choose next because, well, to reach an alignment of 8 bytes, you would need 7 bytes of padding. So first you want to put all the fields that are like 8 bytes long, or that are 7 bytes long, for example, like, you know, something modulo 7. Like, if you have a field with this layout, you want to choose that first. Yeah. I think it makes sense to always choose the best field for that. If that doesn't work, like, let's say, you know, you are somewhere here. now you want to choose the next field, you can still try to choose the next field that yields the minimal padding when aligned to 8 bytes. So in this case, the 2, for example. That would basically mean that you, just by always choosing the field that minimizes the padding you would need to 8, like that minimizes the, I guess, total size offset at modulo 8. Well, kind of flipped around. Well, anyways, the field that minimizes the amount of padding you would need to align yourself to 8, or like the biggest alignment that you still have. If you choose that field, you will often, I think, pair big fields and small fields. And that's something quite valuable. Yeah, I don't know if it's optimal, but maybe you know what. I think the best tactic here is to postpone that, to write a big to-do in there, and revisit this when there was actual code written in Plum, where you have lots of data types in the standard library, and you can actually do experiments and see how the average memory layout size gets affected by these different algorithms. I think that's a lot better than just basically stabbing in the dark and trying to find something that works without actual real-world data structures and usage. Yeah, okay. So let's maybe revert this and just put a to-do in here. The memory layouting is definitely not optimal. Oh, hang on. Gotta switch to my PC. So the memory layouting is definitely not optimal. We should choose, for example, take a look at this. For example, the struct A, maybe int b int will be layouted like this. Revisit the memory layouting once we have actual code and can experiment with layouts and see which are more efficient for real world types than others. Yeah, that's the important part. Like for real world types, we want to optimize that. So yeah, okay. At least, I consciously decided to postpone this. Cool. Yeah, I add a to-do. Amazing. Yeah, there are still some memory layouts. I guess I still think there was something is missing, which we can't do yet. But the only remaining thing to make the compiler work again, is to memory layout closures, lambdas. And to do that, let's just look at, I don't even know. Let's maybe write a map function. So we have a list and we map that using, I think like this. Yeah, using a function that accepts an a, which will be an int, and it returns a plus 1. Yeah, and that's going to be foo. And then we return the length of foo. Like, this is definitely not going to work currently, but I want this to work. Here. Expected equal sign. Oh, true. So this is gonna return an int. Int to int. Oh, yeah, we can't even specify the type. It's always inferred. Okay, it takes an int, returns this. Amazing. Yeah, right, map doesn't exist. So let's maybe add that. So we have a list, you can get the length, check if it's empty. We want to map the list. Which will be a list of t, and a mapper, which will be a function that maps a t to a t, and this entire thing is going to return a list of, oh hang on, that's going to take a list of a, mapper from a to b, and it's going to return a list of b. Amazing. Yeah, so it's going to switch on the list. If it's empty, then it's going to return empty. If it's more of an item than the rest, then it's going to return more of, well, the item, the mapped item. Yeah, let's do it like this. Item mapper, and rest is rest map with the mapper. Amazing. Okay, so there's a to-do in the waffling. That's also good, also nice. Yeah, so we have this that accepts a mapper. Yeah, and if it's more, then we call this. Oh yeah, here we call the mapper with 3. Amazing. Then we call the map function with the rest, and the mapper. Perfect. Then we create a more variant, cast that to the list, return that. Amazing. Yeah, memory layout of plum type. I can guess where that happens. Hang on. Memory layout. Yeah, that's gonna be in the memory layout file. Memory layout of plum type. Well, if it's a lambda, then we want to store the lambda. Well, the thing is that every function, every lambda that takes an int and produces an int should have the same memory layout. But lambdas may need variables from the surrounding scope, and different amounts of variables, different types of variables. So we need a pointer in here. And I think the layout will just be basically 2 things. A pointer to a closure and a function pointer. So basically a pointer that points to some structure that contains all captured variables, and then another pointer that points to the actual function closure machine code. And the lambda just becomes a function that accepts an additional extra parameter with the captured variables. So the size of this is going to be 16, the alignment 8, because it's basically just 2 pointers. And this is irrespective of what the actual lambda is. Yeah. So creating that lambda will be the actual difficult part. Yeah, exactly. Oh, and then a call as well. Like yogurt to waffle. Yeah, so a lambda call would just... Oh, I see, because this is a comp time known lambda. Let's maybe create a runtime known lambda first, and then implement the calling. Like first create it, then call it. So let's say that we have list item, and it's going to add a to that item, a being from the main function here. That's a bit more interesting. Okay, maybe we don't reach a to-do. That kind of bothers me, but sure. Waffling some lambda. Oh no, right. I forgot about that. Yeah, right. Lambdas just get... We don't really support lambdas yet. We just create some lambda, which is horrible. Hang on, the main function. How does that look? Yeah, lambda capturing something, some lambda. So I think we need let's see. Even when creating the yogurt, something, yeah, egg to yogurt, we need to actually do something better here. So we have a lambda, and a lambda has, what does a lambda have? An egg lambda. Has parameters in body. Okay. Let's maybe also get like a unique, I don't know, source. Oh, it has a source, because this is an egg expression. So that's just the same lambda and then the source of the expression, which is going to be, I think, expression or source. And we only do that there. Okay, at least that's good. Yeah, I mean that's still horrible, but you know, at least we know this corresponds to the lambda in this part of the file. And this is apparently one character. I think it's the backslash that belongs to the lambda. And we only support single files for now, so this will be unique for every lambda. Okay, yeah, so we have a lambda capturing something called lambda, and then the file content and the file span, where that comes from. So that doesn't work apparently. Well, let's see how that lambda actually looks. lambda, yeah, it takes a 1, and here we say we call that with 1 and 0, but 0 doesn't exist. That's true. I think the lambdas should contain an extra argument up front containing the captured variables. Like essentially, if we see a lambda captures some variables from the surrounding environment, we put them in some struct or aggregate kind of thing and save a pointer with a lambda. So this will be a pointer to this thing, and then the actual lambda. And the lambda will accept the parameter 0 for the environment or captured variables, or whatever you might call them. So, and how does that work if we have multiple captured variables? Let's just try that out. So let's say b equals 4. And here we actually add a, and then we add b. Yeah. Okay, yeah, no, the lambda just accepts more arguments. That's not correct. That's not correct at all. But okay. So act to yogurt, we need to change that. Yeah, if we have a lambda, interesting. I'm casting lambdas. Yeah, here we have a lambda, and we want to. Lambda builder is something. Then we have the captured IDs. Lambda captures something. And we build up these list of captured IDs. Makes sense. Until now it makes sense. Okay, so from the point of view of creating a closure, these are the IDs. Oh yeah, then we just add, we add new parameters to the lambda, basically. We don't quite want to do that, I think. We want to... We want to... basically create a struct or captured thing instead of individual parameters, So I think we want lambda builder push a parameter, and the type of that is going to be a struct, basically, with captured names, maybe even names, yeah, or IDs, something. Ooh. Mappings in the compiler. Okay, so captured IDs, lambda captures something, and here we want to build like the closure, basically. Closure type yeah, aka the variables that the lambda captures. And the type of that closure is going to be a struct containing fields where each, I don't know, I guess yogurt ID or something is mapped to a type. So this will be closure fields, yeah, will be a list of oh, will be a map, yeah, from string to types. And basically for each captured thing, so for ID and captured egg IDs, we put that ID and the type, which would be the this one right here. Looking up that ID. Yeah, closure fields, the put. And we put in here the yogurt ID type. So this would be this. Hang on, this is like, oh, that's weird. Captured egg IDs. Okay. Lambda captures stuff. I think we don't even need that. Yeah, let's separate this out. Let's first resolve all of that, like get the types and basically build up this captured thingy. And we capture these yogurt IDs. Yeah, that's a lot more reasonable, I think. Yeah, captured yogurt IDs. Yeah, and we basically just do this. Like for egg ID and captured egg IDs, we get the yogurt ID, and then we put captured yogurt IDs, put, oh yeah, we need strings for them. So I think this could be just stringification of the yogurt ID. Yeah. Now let's turn this into a list. Yeah, that makes sense. Maybe push that. Okay. Yeah, so we have the captured yogurt IDs. Next, we want to build a closure. That would be like a struct containing all the captured fields. So let's actually, yeah, let's create these closure fields, which will be a struct. So this will actually map strings to IDs. Yeah, string to yogurt ID, and maybe we could theoretically also say we introduce a new kind of type, you know, in the plum type, like a closure type or something. But I think a struct is fine for now. And yeah, we will need to choose some field names, which can be anything as long as it's unique. So let's actually do that. Let's put the field in there. For captured and captured yogurt IDs means we do closure fields dot put that ID and builder get ID dot type. Yeah. Let's maybe have two closure field types. Yeah. Yeah, I like that. Closure field types, put that. Nice. And closure fields, we're gonna put the ID. Okay. And then the closure type would be a plum type map with closure field types. Beautiful. And the closure would just be this. So we don't have, oh, hang on, this. Yeah, but we don't map these two values. Oh yeah, we're at comp time. Captured, and captured is up here somewhere, maybe. Or maybe not. Oh, captured. A list of yogurt IDs. Now, the closure will be captures should not be an ID in here, but instead something like a struct, I guess. Yeah. So let's actually create a struct. So let's say, basically this builder.push somewhere here. Builder.push, you got up.struct. Hell yeah. With the type of the closure type. Amazing. And the struct is gonna be this, closure fields. Amazing. So now we map fields to, we map, yeah, well, what's going on here? To a type, field types, oh yeah, this should be types, fair enough. Okay, we've created a closure, aka a struct containing all captured fields. And yeah, this does not work because this is already a map. Sure. We put all captured things in the struct. Amazing. Then in here we don't need this because we already have that. We don't need this. Yeah, let's see what we do here. Captured aggregates. we push them to capture things. We do this. Okay. Okay, so in the lambda compiler, we need to add things. But I think we should do that down here. Yeah. So we don't even use that up here. So that's build closure struct containing all capture variables. We do that. Yeah. Now compile the lambda body. Boom. This is where the lambda builder and lambda compiler go. That's the closure as an explicit first argument. Yes. Amazing. So here we push, then lambda captures a push. Oh yeah, we did that for every yogurt ID from the lambda. I think actually we need no lambda hang on, I removed something here. Yes. Yeah, this right here. This is pretty critical. Okay. So we created lambda builder, lambda compiler, and then in here, lambda builder, we push a parameter of the closure type. Boom. And then the closure may refer to egg IDs. So we need to add these mappings here. Oh. Well, yeah, for ID in captured egg IDs, I guess. And also the yogurt IDs. Well, I guess. We basically push them. Yeah, we need to do something like this. I'm not a body to yogurt, and the body takes parameters about me. push the closure. Oh yeah, but we also want to push the other parameters, right? Yeah. From captures. Beautiful. Lambda compiler, egg code yogurt, egg to yogurt. So we push a parameter here, and then for each lambda parameter we also need to push that to the lambda builder, I think. Yogurt param, like this. Oh, I see. Yeah, we don't do that here. Lambda builder push the closure type as an extra, as a parameter. Okay, and then for the IDs, okay, we basically want to like lambda builder dot push yogurt op dot member, I think. Where we want to access from that, I see. So here we have pushed that parameter. And from that closure parameter, we want to access, of course, yeah, we want to access the field, and that should have the type. I don't even know, compiler get, probably compiler dot get of that ID dot type. So this is like a struct access that always happens at the beginning of the closure body. And this does not work, but instead there's yogurt fun. So we need to say fun. Okay. Maybe not. Wait, how do we do that up here? Oh, compiler.lookup. Fancy. Okay, then once we have, hang on egg ID. Yeah, no, we already have that. Oh, builder.get. Oh man. Okay. We basically inserted a lot of struct accesses, like members, at the beginning of the lambda, which extract the types from the closure back out from the closure, you know. And then in here we have the lambda builder. We add that mapping from egg ID to yogurt ID. But not in the lambda builder, but the lambda compiler. Yeah, compiler probably. Okay, yeah, and then we have a list of params. So and we try to lower the actual like runtime parameters. Sure. Oh, you got param. I guess. Okay. Then we lower the body. Okay. Yogurt fun. Ugh. Hang on. Yeah, yogurt fun currently has this in here. Yeah, I think this should just be a yogurt ID. Let's see, build closure, build this, build this. Yeah, and this is just the closure param. Create a lambda that contains both the closure and the compiled function. And a function pointer. Where this is a lambda type with arguments, sure, and a return type, sure, and then, oh man, yeah, if things are comp time, then things get more complicated again, because of course they do. Of course they do. Yeah, I don't know. If this is I'm just gonna say this is false, you know, and just always do this. And yeah, yogurt lambda in here should take captured, it takes a closure, which will be a yogurt ID, which will be a struct, like the closure of the struct. Oh, it actually corresponds to what this up here says. Closure on function point. It's all like almost like it makes sense, you know. Almost. Okay. Egg to yogurt. Oh, right. Oh, right. So this is just a none thingy. Same here. And probably same down there. Yeah. Oh, and it's gonna be closure, right? Yeah, let's call this closure. Mm-hmm. Okay, yeah. Yeah, we can just do that. That's amazing. Now we should like explicitly put them into a struct field. Okay, so there is no matching function named plus for the args. Oh, look at that. Right. But that's not... What? What the hell? Okay. This is the egg, right? Yeah. Yeah, it is. It's not... Yep. There is no matching function named plus for the args int, and something that looks... Yeah, something that very much looks like a closure. There's no matching function named plus. So I think... How does that work? Like, how does that even egg to yogurt? I mean, it's probably somewhere in here. only push stuff to the lambda builder, which I think makes sense, and to the params. Yeah. No matching function. So apparently lookup. Where do we do lookup? We look up main with an int. Okay. Yeah, when converting an egg body to a compiler. Yeah, but this is a different lookup. This is not an egg lookup. This is an egg lookup. And that's it. So in here something is wrong. Argparams is this list of yogurt params, okay. So we'll get the args. Like the plus should not be affected in any way by that. Any way. Yeah. And I'm gonna take a break, I think. Right. So we have this call. Right, with the source. Oh man. Maybe for the source, let's. Yeah, let's improve the printing. Even in debug prints, we also just want to print the range, and that's it. Okay, much better. So we have this call with, okay, plus makes sense. Oh, with two egg IDs also makes sense. But yeah, plus should take two arguments, item and a. But apparently they have, like a has the wrong type because this is egg ID 0. I see what's happening. Like apparently this a refers to the first argument of the function, but the first argument is somehow, you know, implied to be hang on, this actually makes sense. Like this closure right here. The a should be parameter number 0. But we should get the captured thing from that, not just directly, you know, directly take that. Okay. So the mapping is somewhat wrong. In here we said I'm the compiler at mapping from some egg ID to the yogurt ID. things. Only contains what fields? Egg to yogurt. Interesting. Well, yeah, I'm gonna take a break and then we'll see. Okay. Let's maybe close this because this is not needed anymore. Yeah, why do the closures not work? That is crazy. Captured egg IDs? Yeah. Captured yogurt IDs. Oh, I see. I see. Inside of the closure, rather than, you know, getting the yeah, rather than mapping this to the original yogurt ID from the surrounding scope, we instead want to map the egg ID to the yogurt ID of this struct. So basically, you know, we get some sort of value out of the closure and use that. I think that's a better way to do that. Oh, hang on. U1 is not on the map. Okay. This is strange. So we have a lambda. Takes one argument, 3. And then there are these. That does not look correct. Why is it that way? Okay, so we say lambda builder.push. Do we need to push that to some yogurt body as well? Maybe. Yeah, builder.push is what we say here. Oh yeah, that makes sense. Builder.push is what we use all the time. And the builder is a yogurt fun builder, just like the lambda builder. So when we say, you know, lambda builder.push, this expression, why does that not appear in the body? That member expression. We are an egg to yogurt, yeah. And this is the yogurt. Okay. So inside of the lambda, I would expect something like, you know, X is the member of some closure. But why does that not work? I don't get it. I really don't get it. lambda builder push. What? I mean, it even references 1 and 2. And yeah, I get that. Like, this doesn't work. Sure. But why are they not in the body? When you say push on a yogurt body builder, you push that to the body. So why is that not there? That doesn't make any sense. Oh, hang on. In which function am I? Please tell me I'm in... Yeah, expression to yogurt, okay. Not a value to yogurt. Okay, so here we have some ID. I get that. And then in the end we say, well, in the end we say, let's push that to the body. To the body builder. But how does that work for like functions? Yeah, this exactly. We have the functions. This is some code function for the yogurt fun builder. I will just say body to yogurt. What? That's crazy. I don't know. I really don't know what to do here. Build a closure. Create a lambda builder. Lambda builder. Not push. It's a fun builder, not a body builder. Okay, maybe we need to push that to the body as well, like and how does that work for, how does the body do that? An egg body using a yogurt fun builder, what it does is pushes something to that builder. Okay. And then we add something to the yogurt body. Okay, what happens, like how's the yogurt body created here? We create a yogurt lambda using some function. The function that we added here, where the body is the lambda body. Ah, that's just the body converted to yogurt. So this is just not designed for that, I guess. So 2 yogurt on a body. For now I'm just going to copy that code from here and move that down somewhere here. Lambda plum. Yeah, basically we want to build a yogurt body. Yeah, I think this makes no sense. Yeah, we have the closure param, sure. And this is essentially what we want to do down here, right? Pushing pushing the explicit parameters. So this would be lambda dot, I don't even know, args, something like that. Yeah. Params. Yeah, we don't do this. I think. Instead we do that up here. No. So basically the lambda params means we get some lambda param and yeah, we push an ID. Sure, we add a mapping for that. Amazing. Yeah, not builder dot push, but lambda builder dot push. Oh yeah, this will just be that. So we have the closure param, then we have the other params. each of the explicit params we add the egg param dot type, I think, I hope. Something like that. Other params dot push yogurt ID. Why does that not work? Because this is not mutable. Sure. Other params, push that ID. This would be the lambda compiler. Add a mapping from egg ID to yogurt ID. Sure. So now the parameters are there in the body. And next we unwrap, like we extract the captured parameters from the closure parameter. Yeah, that's amazing. Okay, this doesn't work because egg ID is a param. Oh no. Dot ID maybe? Please tell me that exists. Nope. It only contains name and type. Those don't have egg IDs, yeah. What? Like what kind of egg IDs do they have? And where are they if not in the params? Hang on. Yeah, this is the egg. In the main, here we have the lambda. Takes an item, which is an int. Yeah, and you can see it takes a 6. Okay. Sure. Where does that come from? Egg. It has params. Oh, it has a body, which then has parameters. Oh, I guess. Yeah, okay, so lambda dot body dot params dot get. Sure. Nice. And then we have expressions. Oh yeah, and these right here are also, like they should also be added to the expressions. So basically expose dot push minus value and for each egg ID in the lambda body expressions, we'll convert that using the lambda compiler. Yeah. Okay, yeah. And this doesn't work because this is probably not... Oh yeah, some things need to be mutable, I guess. Like that. compiler.addMapping. Okay, and in the end we have a body. Yeah, And the params are actually interesting. Is other params used anywhere? Nope. Nice. Oh yeah, that's true. Just do that, I think. Yeah. Yeah. Then extract the function here rather than the body, and then we can do it like this and be like, yo, this is the lambda function. The lambda body into a standalone function. Hey, hell yeah. And then we have the lambda function. Amazing. Okay. Yeah. Ooh. I mean, on yogurt fun, I think there's a return type function, so you can just do lambda function dot return, well, return type, like that. This call doesn't work. Oh, and a yogurt signature. No. Where are they added? The compiler.yogurt.funds. Oh yeah. Yeah, that may well be. Because instead we have the lambda function. I mean, yeah, we could just name that function, I guess. Because why not? New error. Okay. Hang on. Let's first check if this is actually correct, what we have here. Okay, so there's the lambda. Oh, look at that. Lambda which takes an int. So in here it actually takes a closure and an int. And then from that closure it accesses the fields 0 and 1 to get back some other things, some capture variables. Hell yeah. And then in here we just take 1, the explicit argument plus the closed over thing, and then take that and add some other closed over thing. That's amazing. And when we call that, or when we create that lambda, where's that? That should be somewhere here. Here we create a lambda. Oh yeah, with capturing 6. Oh, and 6 is not yet here. So that is not good. Oh no. To yogurt or an egg expression results in... Oh yeah, we just want to add something to the body, I think. Yeah. Yeah, exactly. So let's do... Let's do that. I think that's up here. Captured variables, we map them, we build the closure. Yeah. Right here. Do we use that closure somewhere? Probably right down here. Yeah. Okay, so what we want is to also add that to the body. So body dot push. Yeah, we probably don't need that. Oh dang, everything is super stupid. I don't know why though. Well. Let's see if that's better. Oh, hell yeah. We want to create a closure, so we create a struct containing all captured variables. And then we create a lambda where we save that closure. Boom. Amazing. Then we call map. And then inside of map, down here, we, well, for the more thing, here, we call that closure with 3. Nice. And like that's failing in the, yeah, when converting that to a waffle. That makes sense. So let's look in yogurt to waffle. And here, when we have a lambda call, what we actually do is, well, the call, lambda call has a closure, and we want to get the function pointer of that. Okay, now we want to do a waffle call at some point. That's a given. And the question is, what do we want to call, and what do we want to call that with? The call probably has some, not receiver, but I guess function. And function, okay, not a function, but a lambda, yeah, exactly. And that is some, you know, some ID probably. So we want to convert that to the waffle as well. What do we do with the, oh no, we just get that. Oh yeah, that makes sense. We just get that from this mapping. And then from that we can get the closure and the function pointer. Yeah, closure is lambda dot waffle member at offset 8 length 8 alignment 8, and the function pointer will be, oh, hang on, like this actually. Closure will be at offset 0, the function pointer, like new closure pointer will be there, function pointer will be somewhere else. And then here we do a waffle call of a waffle signature. Well, that's not quite. We have a separate waffle lambda call, right? I think so. Well, damn. Okay, and a waffle expression, and then some integers. Sure. Yeah, the arcs are basically, yeah, we want to lay out them. Build an aggregate. Do something very similar to this, actually. So the first argument here is a closure, which is not really a type. Ugh. So I think I'm just gonna say one type dot int, I guess. That is like a type int, right? Yeah. And we push all the other argument types. That is our argument layout. Oh, because ints have the same size as pointers, so that's why, yeah. I guess. Then we have waffle parts. That's a waffle expression. A list of expressions, okay, sure, yeah, we build in a waffle aggregate based on that. Makes sense. And then the return layout. Let's see what funs get call the function. Yeah, we do have a function pointer, you know. Oh, yeah. I should probably switch to this. If the index is 0, then we want to push the closure pointer and unbox that. So waffle unbox. Oh, hang on, not unbox. No, just take the waffle. Just take the closure pointer, actually. Otherwise, we get the argument from index -1. Oh, amazing. Call a function pointer, I guess. But we need some way to call a function by some runtime info. Oh, that is tricky. That is tricky. Okay, I do think we need some sort of call indirect, something like that, in the waffle as a new primitive thing, call indirect. Yeah. We basically have a function pointer which is a waffle expression. that does mean that down here we have to deal with that called indirect of some call, I guess. And it's going to be similar to this one. Set, this is going to be, well, call it, okay, yeah, it's going to be exactly that one. Yeah, and maybe let's also call it function. Hang on. Oh, well. True. Amazing. Only contains these fields. Function is not a field on yogurt lambda call. True. Yogurt to waffle. Function pointer. Yeah, I think the yogurt lambda still needs to, does it store the return type maybe? No, it does not. But the lambda does. No. Lambda call. A lambda is something with a yogurt ID, okay, and that has a type, right? Oh yeah, plus we can just get, well, basically expression.type. I think. Yeah, indirect, where the function pointer is function pointer. I think for call indirect, the hang on, let's look at the bytecode. I don't even know if we have something for that in the bytecode. Probably not. And the bytecode is in the VM, I think, yeah. So call with another address. Also want to call indirect. Yes, that's basically call with a runtime null address. No longer a to-do. Post an address calls another function. Amazing. They don't handle call indirect. True. I don't. you know, in the malloc we also just do casts. So I think here we do the opposite thing, casting an int to an address, and then basically doing this. Nice. So calling lambda actually compiles apparently because of the map function. You know, the map function compiles. Yeah, then so creating a lambda, what would that do? I think it would basically something like lambda dot Do we need something new in the waffle for that? For creating a lambda? Seems pretty high level, that concept, you know. Like we create an aggregate containing the captured things like the closure, and then a function pointer. Yeah, function pointer is basically the remaining thing. Waffle signature. Yeah. Okay. I guess. Getting the function pointer of some function. That's the idea. Ooh, this is not elegant. Yeah, but basically, because we know the bytecode instructions, the layout of bytecode instructions, we know that. We know that for bytecode instructions, this is an enum, so this will first contain the payload, and then a tag telling us what kind of thing there needs to be. And for a call, it just contains an address. For push 8, it just contains an int. And in this case, we'll just overwrite both of these with the addresses. Whoa, that is nasty. Okay, so expected an opening parenthesis. That's true. Yeah, so here we can cast that bytecode instruction to something that expects an address, because we know that every bytecode instruction that needs to be patched just contains an address in the payload. So we just ignore the tag that's, somewhere later on in memory, and we just have this bytecode instruction. Function pointer. It's not. Function pointer. Oh. Now what's this? Yeah, there's a function pointer waffle expression. Oh, I see. But there's no new function pointer instruction for that. That makes sense. Just use the push instruction. Okay, to do implement lambda. But now we can actually do that. To waffle, so load to waffle. Yeah, we have some lambda. Now we want a waffle aggregate containing the lambda closure. As well as the function. Yeah, the closure is already been compiled, so we can just do that. Waffle function pointer is something still need to create. Yogurt. Oh, it has a yogurt signature. No. But that was like a very stupid conversion, I think, from normal signature to waffle signature. Yeah, exactly. Okay, yeah, I mean that it's totally fair that things are not working because alignment stuff and crazy things. Well, let's just see the waffle. So waffle has in particular this lambda, which receives arguments. Oh, and this will contain both the closure, which again contains two ints, and it will contain the actual argument, like a captured two captured things. Hang on, take something at offset 0, 16. Oh yeah, that's the captured thing. And then at offset 0 and offset 8. These are the captured variables. This is the closure, these are the captured variables. And then in here, it takes something at offset 16 size 8. So something after that. That's the int, the explicit argument to this lambda. And it adds the first thing from that closure. No, okay. I can see where this is going wrong. Okay, well, let's maybe start from the main function. So in the main function, we want to create a closure, but it turns out the closure uses variables from the outer scope. So what we do is we take 0, 8. We take the argument and some value from here that was used. We take those and put them in a struct. This is the closure. Then we create a lambda, which contains a closure and a pointer to the function lambda something. Really nice. And among all functions, all lambdas that take an int and produce an int, the layout of this will be compatible. So it will first be, oh hang on, no, this is already wrong, because this should be boxed. There should be a pointer in here. Ah yeah, things will crash in the end, but yeah. Okay. Crazy. Okay. Yeah, so we create a closure, and then we create a lambda, which has a pointer to the captured variables and a pointer to the function. So just 2 pointers, 16 bytes. That's every closure has that same layout. And then we call map with, 5, which is this list, some padding, and this closure struct. This lambda, basically. Where's map? Map is up here. What map does is, in here, when there is something to be mapped. Oh dang, that is some crazy shit. We take from the arguments an offset 24, something of the size 16. And I can guess what that is. Like, hang on, this is 5, this is a list. List has a size of 17, list of int, yeah, because it contains, it's basically this type right here. So it's an enum of empty or more, and here the payloads are an int and a pointer. So 8 bytes, aka 16 bytes, and then 1 byte for the tag, aka 17 bytes. 17 bytes plus another 7 bytes is 24 bytes. So the closure, or the lambda here, is something at offset 24. So here when we want to call the closure, from our arguments we get the thing at offset 24, 16 bytes. Because again, a lambda is just a tuple of a closure, a pointer to the closure and a pointer to the function. And we take the function pointer. We dereference that. Like you say, hey, this is an indirect call. That's not really a dereference, it's more like, And we call that with the closure. So from our arguments at offset 24, 16, that's the lambda. And the first part of that, this is the function pointer, this is the closure. We pass that as an extra argument to the actual argument that we have, which is this int right here, and that's like the thing at offset 0, size 17, aka this argument right here, and offset 0, 8, that's size 8, that's the int. So we call that closure. Crazy. Then we call map with, dereferencing the pointer that was in this thing, some padding, and then the lambda. That seems correct. So now let's look at the lambda, and I think this is not correct yet, but because this assumes something. Oh yeah, tries to get the captured things out of the map directly, while in reality we're at the waffle. Yeah, this is correct. This is correct. Oh, I see. When converting a function to expression, function builder, ready to waffle. Fun to waffle. That's weird. That's like interwoven in all. Ooh, I think this is like wrong in the yogurt still. In the yogurt, the lambda here. Yeah, just as normal struct access, and the type of this is the closure type. Which is correct for type checking, you know. I think we need a separate concept of closures, maybe, or closure expression or something like that in the yogurt. Yeah, I'm afraid so. Something where we can say, hey, this is a closure. And then we know that this is a pointer, basically, something like that. Oh, yeah, I don't like that. Yeah, I'm gonna stop for today because it's pretty late, but well. Hi there. So, yeah, in the meantime I got a cold, so I'm not gonna talk too much, and if I like cough in between, you know, that's just it. Yeah. I'm not entirely sure how to continue here. Like, I feel like I'm gonna make myself a bit bigger here, but I feel like I'm stuck in this memory layouting for some time, and things don't work out. Like, the only remaining piece basically is how to do lambdas, and turns out that's really, really difficult. So we have new concepts in the waffle, like, you know, function pointers, taking them, and indirect calls and whatnot. But I feel like the abstraction kind of leaks in the yogurt, because in the yogurt a function can have a closure, which is, you know, just some expression. So, you know, it has a yogurt op, and that's, you know, a parameter or a struct or something, probably a struct. Maybe, I'm not entirely sure, but definitely something of the plum type struct. And that's probably not the right abstraction here, because functions, if you access a member on that struct, when we convert that to the waffle, that shouldn't just be a normal struct member access. No, closures are different. Closures are always allocated on the heap, like the, yeah. So that's not actually correct to insert a member expression there. I think we would basically have to either have a new kind of yogurt op that is like a, I don't know, closure member access thingy. Either that, or we revert the change of having a single object for the closure instead of having closure values in here explicitly. And I'm really not sure what to do about that. Like, semantically, I think it feels... I feel like it is more clean to have separate values here. Yeah. This is difficult, really, really difficult. So we won't, our lambdas in the yogurt fun, they will just store the captured variables. And there will be no concept of a closure object that is somewhere in memory and contains those captured variables. I'm not sure how to do that. Yeah, I'm probably gonna... Let me maybe revert that, We do that here. You get lambda. Yeah, no, this actually has captures yogurt ID, okay. Hang on, is that called capture? Yes, make it consistent. Captures. Captured or captures? Captures is fine, I think. Yeah, and then here, let's revert that to do stuff. And the captures. Beautiful. Oh man, yeah, I feel like I'm going back and forth between these different approaches, and it's really difficult. Like, in the waffle, I think I have basically found a nice abstraction of how to model lambdas and closure. Yeah, should update this. Anyways, how to model lambdas and closures and so on. I mean, closures don't exist here, but we have this way of getting a function pointer to some function and then calling that function in an indirect way. That's pretty amazing. That is really amazing. Yeah, waffle call indirect. Makes sense. Yeah, okay. So at least I figured that out, And I feel like a lot of this low-level stuff right now, I haven't done anything like this before in other languages. I feel like in the entire parsing, the entire like transformations and type checkings and so on, like that's, to me that's like second nature. I can do that in my sleep. But this low-level thing of, hey, where do we allocate closures, and like how do we represent that in the different compiler stages? I don't have as much experience with that. So this is for me, also just figuring stuff out. And I mean, if you're watching these unedited development sessions, you're probably okay with that. But I just want to explain why this takes so long, figuring this closure stuff out. I don't have much experience doing that. Alright, yeah, we have these kind of constructors, sure. We have this, we have that, okay. There's also like to-do update. Because we have updated the syntax over time, So, yeah. What's going on down here? Oh yeah, that makes sense. Okay. Okay, the waffle seems fine. So the only thing remaining is yogurt to waffle. And we need to map that somehow. When we have a lambda, I can see here that we have some sort of waffle box. Yeah, and we want to put those things here in a struct, basically. So let's maybe look at how structs are created, and we're gonna do the exact same thing, except for the close over things. Well, being sick. Okay. Okay, so we don't actually have a type for that. That is not optimal. Maybe I should write a write a helper function for that. Closure type, something like that. Returns takes captured yogurt IDs, I guess, and returns a type that basically is the layout of those. Yeah. And I should maybe also say this takes some yogurt, some fun, I guess, some yogurt fun. Yeah. And maybe let's look for when we create a yogurt. Yeah. And we create some sort of struct here. So yogurt op.struct. Hang on, I thought I should create that somewhere. Yogurt op.struct. Huh. Alright, when creating the act to yogurt. This is what yogurt op.struct. Yeah. Okay, so we cast things apparently. That's definitely interesting. Okay. Yeah, we don't need to cast anything in our case, so that's... Oh, we're in the cast function. Okay, so struct... Oh, hang on. Yeah, this is... Yeah, build the closure. Okay, yeah. Right. Figure out which variables the lambda captures, and look these up in the current scope. Capture yogurt IDs. Okay, so we build a closure. Yeah, we want to move that. Basically, we want to move that into one compiler level lower, in the yogurt to something, yogurt to waffle. You know what, let's maybe first inline that up in where we actually use that, and then we can see what parts are common among creating a lambda and calling a lambda, and then we can factor those out later on. So we want to create a lambda. Okay, so we want to build the closure, a struct, a heap allocated, struct containing all captured variables. Beautiful. Okay. This allows lambdas to have a uniform representation consisting of a pointer to the closure as well as a function pointer. Okay, so we have these fields from string to something interesting. I mean, sure. And we have these types. And basically we say lambda.captures. That are some IDs. And then we put those IDs. Okay, yeah, we add things to these maps. I mean, sure. You know. And this will not be builder, but actually fun. Look at, I think. Yeah. Yeah, the closure type is just a struct. And yeah, and here we basically want to do the same thing that we do for structs. We want to do that. You know, closure type. That instead of this, we're actually doing this. We're layouting that struct. You know, instead of, instead of pushing this yogurt opt.struct, and then later on in this compiler stage we look at, oh, this is a struct, so let's layout stuff. No, we do that directly and separately for the closure, which I think is fair. Yeah, so we don't do this. Let's maybe just comment that out for now. And we take that closure type and memory layout that. And for each part, we then push stuff. Yeah, we don't do this, I think. Yogurt ID to waffle expression. Maybe we do that. Yeah, we probably do that. Struct get of that name. Oh, those are the strings in here. You see? Yeah, okay. So this is really just closure fields instead of struct fields. Yeah, that makes sense. Yeah, we basically push those. Okay. And then we aggregate those. That's basically the closure. You know, just a waffle aggregate of those things. Yeah, that seems right. That seems right. Yeah, and this will really just be be a waffle aggregate of a pointer to the closure as well as a function pointer to the function. Perfect. Like this is actually quite, I don't know, high level, I guess. Yeah. Okay, seems correct. And then when we call a function, basically nothing changes, you know, we still get the closure pointer and the function pointer, and we get that, we put that as an extra argument somewhere, so sure. But when we convert the egg to yogurt, we no longer do this. You know, a lambda doesn't, we don't build the closure here yet. But instead, yeah, we don't have this extra, you know, this closure param right here. Yeah, but instead, we just push those to the function, or like to the, I'm just gonna call this captured. Captures, maybe. Yogurt expression, yogurt IDs, yogurt IDs. And we basically want to do the same thing for the captured variables. Oh yeah, and that's what we do down here. Kind of. expressions is something, yeah. Oh yeah, we don't do this. Yeah. So we first add the captured variables. We make them basically available by adding mappings to them down here. Yeah, let's maybe look at these in a bit more detail. So for IDs in captured egg ID and captures, which is, yeah, totally inconsistent naming, but blah. First, gonna get this to work at all. Yeah, we don't actually push yogurt member or something, but instead we push a parameter type because we just assume that those are available. Yeah, I'm just gonna paste that in here and then see what kind of, what parts we use as well. Yeah, there's not gonna be a yogurt member, but the type here is correct. So this is not gonna be params types, but it's just gonna be the type of the underlying captured thing. Yeah, we have no extra expression in the closure that unwraps these local variables. That will happen in the conversion from yogurt to waffle. Basically dereferencing these captured variables and like copying all of them from the closure that's on the heap somewhere to the stack. Okay. Yeah, we have those. I guess, yeah. And then we build the actual expressions. Sure. We build this stupid body thing, and then this doesn't have a closure, but just captures some. And here are the captured variables. Yeah. Yogurt fun, maybe a list of something. Oh yeah, no, captures dot to slice. Okay. Yeah, a couple of things are not working, so yeah, what I was actually curious about was how do we call a closure? Collect cap. Oh, yeah, no, that's not. Yeah, lambda call. Okay, something. Sure. Yeah, captures nothing. Beautiful. Why is this not working? Like we have the captured variables. I guess the yogurt lambda just captures as a thing. As the variables it captures, which is supposed to be slicing. And there's a recurring theme. I'm just gonna move that up. Where we define those, where we aggregate those. Okay. Yeah, basically undoing a lot of the things I did before. Hang on, I can just, typing that would have been faster, but oh well, yeah. Yogurt fun captures. Oh yeah. but typing it out doesn't prevent me from making these stupid mistakes. What's going on up here? Oh yeah, same thing. There's gonna be a slice of yogurt IDs. Or rather, no slice of yogurt IDs. Okay. And down here, yeah, just undo that. Cool. Oh, amazing. Oh. Captures or captured? I think captures is more... No, this function captures. This is not like, not as temporal as having, yeah, having different like time forms in there. Yeah, let me maybe put them in the right intuitive order. Okay, yeah. So let's maybe look at this yogurt waffle, and especially the lambda. Oh no, the lambda call is completely fine. The thing we need to adjust is when compiling a function, which I think is turning a yogurt value into waffle, turning a yogurt expression into waffle. Amazing. A yogurt body. And now a yogurt function. Yeah. Yeah, exactly. And this is where we need to think about captured variables. Like, how do we, where are they on the stack? How do we do that? Yeah, so when you call closure, hang on, when you call a lambda, let's maybe draw something, you know, or like write something. When you call a function, we expect the parameters to be on the stack already. We expect the parameters to be on the, to already be on the stack. You know, we have your stack, and then param 1, param 2, or param 3, you know, layouted efficiently as an aggregate. Yeah. For closures, hang on, for lambdas, yeah, we then push all like, we then, yeah, for, hang on, for lambdas, one of these parameters represents the closure, a heap allocated object value, I don't know, containing all captured variables, values, containing all captured values. Yeah. Before lowering the function expressions, we copy, yeah, those captured values from the heap, from the closure on the heap, onto the stack. Amazing. Okay, that's basically the idea. Captured 1, captured 2. Something like this. Yeah, that's the general plan, you know. So we have the params and the param types. That means we know the kind of yeah, these are the parameters that are explicitly expected. I'm just wondering, when you call indirect, yeah, hang on, call lambda call, yeah, lambda call. Here we take the closure pointer, okay, yeah, and we lay that out on the stack with the arguments that we provide. That is something I had not considered, I think. Hang on, how does that even... You get the argument types, okay, yeah. You have some sort of call. Then for each argument and the call arguments, this should not include the closure, because there is no concept of a closure in the yogurt. We push that to the archetypes, okay, but then we lay that out directly. I think we also want to add an archetypes dot add basically a plum type. Is that like a plum type opaque or something, like a, you know, for a pointer basically? Not really. Primitive int comment to like this is closure pointer to do better type. Yeah, something like that. We want to lay out a pointer, like add a pointer as an explicit argument to this. And then we lay all the arguments to the function out, including the closure pointer. That's the important part. And then we have these parts, and for each part we do something. Yeah, now this is a bit more easy, I think. You know, if index is call args.len, then this is just going to be the closure pointer. Otherwise, it's going to be index. So yeah, this makes this a bit more easy, you know. Yeah, rather than index 0 being the closure, it's just, you know, the closure is somewhere in there. And okay, that seems sensible. Yeah, we aggregate that, we call indirect, and with a function pointer and the arguments, which includes the closure. Perfect. And that means that I'm just going to copy this. You know, that means that down here, where's that here? Yeah. When we want to compile a function to the waffle, we can basically assume that the closure is also in there. You know, so for lambdas, one of these parameters represents the closure, a heap allocated object containing all captured variables. Yeah, param 3, closure, param 2. Yeah. Represents the closure pointer, one of it represents a pointer to the closure. Yeah, closure is the thing on the heap. Yeah, and we have a pointer to that. Closure pointer. I don't know, something like that. Exactly. So then in here, yeah, you know, we memory layout, all of that. In reality, we also want to do something that's like copy pasted from above. Yeah, we don't want to do this, but when we call a function, we provide these arguments and we think, okay, how should we lay those out on the stack? And we do that same layouting in this waffle function. And that is the guarantee, you know, because the layouting is deterministic, we know that the function expects those parameters in the same layout, in the same order as when we call that function. And we want to do that same thing with the params here. So basically, you know, if this is a closure, so if fun.captures is sum, you know, if it captures something, that basically means it's a closure. That exactly means it's a closure. Captures is a maybe of a slice. So if it's a lambda that doesn't capture anything, that will be sum with an empty list. Whereas if that's a top level function, and like not a first class function, you know, then this will just be empty. And then this will be none. Okay, so if this is sum, then this is a lambda, and an explicit like first class function kind of lambda, instead of a top level function. In that case, we add this closure pointer. That's an extra parameter that we can expect to be on the stack. We lay those out, perfect. Then we basically do this in the calling side, you know, putting all those things on the stack, on the stack in the right order. Now we want to do that opposite thing. Like now we are inside of the function. We know those things exist on the stack. Where do we do that? Oh, here. Let me see. Oh yeah. Okay, so for each parameter, we basically just say, hey, by the way, you can get that parameter by just getting, you know, the member of this param layout thing. And we basically want to do something very similar for the captures. Yeah. So, you know, if what was it? Fun.captures is sum. Yeah, you know what I'm gonna add? Some disclosure or something. Oh yeah, in this case, we actually want to use that. So if it captures some IDs, then we also want to make those IDs available to the body of the function. So we know the fun.get. Fun is fun. Yeah, captures. Yeah, basically we want to iterate over them. That's maybe the first thing. Oh, we want to. Oh, I see. We want to lay out the closure itself. Oh, yeah, we have the param layout. That's, you know, the layout of the parameters that we are passed. And now we basically want, yeah, let me maybe not I'm gonna skip over this and do the actual like interesting part down here. We want to somehow get the like this is some to do. Yeah, and here we just get, you know, for each of the captured values, so for each ID, I guess, and for each capture and the things that it captures, this is an ID. We get that corresponding expression from the function. That is the type of that is actually the type of the variable that gets captured. We memory layout that, and then we know that, hey, if you want to, you know, access this yogurt ID that is from the captured variable, you actually need to use this waffle expression. That's what this yogurt ID to waffle expression represents. And basically, for each capture, yeah, this is just the ID. And what you need is basically the closure. So we'll have some sort of, you know, closure layout, and then the actual closure is gonna be something like this, like, what was a param aggregate? Yeah, like the closure pointer, you know, like the parameters contain a pointer to a closure. So from that parameter aggregate, we can get what even is this? We can get the param layout, yeah, here, where we have added that int, so that is params.len, param to offset, is that it? I don't know, field, capture to offset, how is that? Capture to offset, interesting. Anyways, we can get params.len, because we know that, you know, we added this extra pointer thing for the closure. And that pointer has a size of 8 and an alignment of 8. And then the closure is going to be waffle unbox of that. Yeah, please unbox the closure pointer using the closure layout size and the closure layout alignment, like this. Yeah, that's the idea. If this is a lambda and it captures some variables, then, you know, we add to this how we can access those. And the way we do that is by, you know, getting the closure layout, which we need to do still. But then we know that somewhere in that parameter aggregate, there's a closure. You can even move that up here. Yeah, we can always get that closure pointer. And yeah, we basically unbox that. So, you know, we copy that from the heap to here. And then for every captured variable, yeah, we can make that available by getting from that closure, so this will just be closure, a member, the member of, you know, closure layout thingy to offset of that index. Yeah. Yeah. So the remaining questions, like, what's the closure layout? Well, that should be the same layout as what we created up here when creating the closure. Like when we create a lambda, we also create a closure for that. We allocate something on the heap. Yeah. And that's just memory layouting a struct, basically. So build a closure. Yeah, and this is something that I think we should factor out. Memory layout struct. I think we should maybe, just maybe, also create a memory layout closure, which is just a simple wrapper maybe even around memory layout struct, but you know. Let's see, so memory layout has an aggregate layout aggregate, okay, sure. Layouting arbitrary type, function parameters, structs, yeah. Yeah, this is just some types. Closure will actually be pretty similar. Layouting closures. Yeah. Let's copy that down here, and then we have closure layout, amazing size and alignment and parts, which are closure parts, and then capture to offset, basically. Closure part can be captured. I'm not happy about the, no. It is captured. Well, I don't know. Memory layout. Closure that captures these types. I'm gonna call it capture, the capture. Nah, I don't know. Weird. So yeah, we have a list of memory layouts. Sure. And for every capture thing, we push that, sure, and we layout that. And then we map those. So if there's a field, there's actually like a closure capture thing. And boom, we have a closure layout, yeah. I'm just realizing like this is mostly the same thing as this, with different, you know, terminology and stuff. I don't know, maybe but that's probably fine. Yeah, it makes the, at least it makes the code really readable. Yeah, because now we can just say, you know, rather than having to, I don't know, what even is this, like create temporary strings and then that's just a stringified ID and then getting that later on, we can just say, hey, we have closure fields, which is lambda captures is just a list of IDs. So closure fields, yeah, okay, that's actually captured types, maybe. Yeah, captured types dot push that type. Amazing. And then the closure type is not actually like a thingy. We can just say closure layout is, you know, captured memory layout closure. Boom. And then for each closure layout parts, this is either a capture with an index, and then we just say get lambda.captures.get index, like that. Oh yeah, this is supposed to be a list, I guess, of that. Yeah, 2 slices, probably. Okay. So we have that. Really a bit more readable. And then we create that closure, and amazing. Okay. So we kind of want that same closure thing. Well, this part up here, I think, is the relevant one. We want to use that down here. And closure layout is to do. Yeah. And here we can just say, you know, we get the types of the captured variables. That would be closure captures is captures. Captured types. Yeah. Captures. Do captured types get that thingy? And then we say closure layout is captured types.toSlice.memory layout closure. Boom, we have a closure. And then for each captured variable, we memory layout that. Then from that closure layout dot capture to offset, beautiful, and we get that index. Okay, this seems like it should work, which is cool. Yeah. Okay, so we have the body. Oh man. Body to waffle, blah blah blah. Okay, yeah, and we don't actually need this. Yeah, let's maybe test this out. Like I'm sure there are some cases where things do not work well yet. Yeah. Oh, yeah. Okay, so something doesn't work. To waffle on something. Body expression. Okay, when converting the map to a waffle. The map. So that would basically mean that down here, you know, we try to convert the map function to a waffle. That's what you can see down here. Yeah, let's maybe print out these just to make sure that, you know, before just do like this. Yeah, before even like going into the body, that the parameters and captured variables get extracted correctly from the stack. Oh, yeah, let's maybe debug print that, I guess. Okay, boo, that's a lot of stuff. Okay, so the waffling the map function basically means this. You know, yogurt ID is, hang on, let's look at the yogurt first. Map, we're looking for map. Here's the map function. Takes two parameters. Nice. Yeah, this list, and then this map from int to int. That's cool. So far so good, I would say. Yeah. Okay, and then it actually switches on that list, which is a linked list enum thing. If it's empty, then we'll just create an empty thing, cast that to a list of ints, and you know, if it's more, then we have the item and the rest of the list. Here we call one, so the mapper with that item, and yeah, we get back some new mapped item, and then we call ourselves recursively with the rest of the list and that same mapper that we called here. And finally we create a more node, basically, using the mapped item as well as the mapped rest of the list. Amazing. And then we cast that to the correct type and return that. Okay, then we cast the entire thing and return that. Okay, that seems fine to me. So let's look at the expressions that exist. Yogurt ID 0, that was the map. That is a waffle expression of size 17. Correct, yes. Like 8 bytes for the item, aka the int in the variant, then 8 bytes for the pointer, and 1 byte for the tag, more empty than those other 16 bytes of just padding. And the kind is a waffle member of something, of something. Of something. Okay, hang on. What do we do here? We know waffle ID 0 just exists. And waffle IDs, those are the local IDs, basically. Yeah, of local function, local things. And waffle ID 0 is always the argument to the function. Yeah. At offset 0 in those arguments, apparently we have this. Oh no, I see. So all the arguments that this function expects, together they have size 40, which is quite a lot. Okay, let's see, size 17. We probably have some padding to like size 24, and then we have the actual closure. Yeah, our arguments contain this and that. This is 17 bytes, then we have 7 bytes of padding to offset 24, and then we have this closure, which is just a pointer, a lambda, which is a pointer to the closure as well as a function pointer. So 16 bytes. Yeah, 24 plus 16 is 40. Yes. So these are just our arguments. So this is the argument expression. And from those, we now access a waffle member at offset 0 of size 17, alignment 8. So this is, you know, basically from this thingy, that aggregate containing all our arguments, we now cut out only the first argument. And that is what we know as yogurt ID 0, which is exactly correct. Yeah, yogurt ID 0 is supposed to be this argument. Yogurt ID 1 is probably something else. Hang on. Yeah, yogurt ID 1 is, you know, from that same expression, from that same argument aggregate, we now get a member, but at offset 24. That's the lambda. And that member has a size of 16, aka closure pointer and function pointer, alignment 8. That seems correct, first of all. Okay, yogurt ID to waffle expression. That seems really cool, actually. Okay, and then we call to waffle. On a body, okay, makes sense, the function body, and then on some expression, probably the switch, and the switch contains bodies for every case, and then in one of those we try to access something from a slice of yogurt IDs. Try to access something from a slice of yogurt IDs. Okay, let me just search for okay, that's a lot of irrelevant get thingies. Well, the question is where? Where does that happen? You know, probably. And what is this function here? To waffle of yogurt value? Nope. To waffle of yogurt expression. Yes, that's what broke. So somewhere in here, something breaks. Amazing. Let's see, this is a map. This is a map. I'm just looking for the get thingies, you know, function is a function. Nope. And we call get on a slice. That's interesting. Member.off is, yeah, you know, so this is a function, this is a map, this is a map. Yeah, this is memory layout enum. Yeah, this is a map. This is a map. This is variant payloads. This could be it. I think the easiest thing is just to print the expression operation and see what happens. Okay, so we have this lambda call. Okay. So we call some lambda, yogurt ID 1. Okay, arguments is yogurt ID 3. Sure. So what we do then for a lambda call is this. We get something from the mapping, like yogurt ID, hang on, yeah, call.lambda, aka this 1 exists in the mapping. Yeah, we saw that before. And we get the closure pointer, function pointer, sure. We get the argument types. Maybe this breaks. Call that args.get. Would be weird, but worth a try, I guess. Okay, let's just print the, like, you know, print the parts, maybe. Oh, hang on. It may not even need debug, resulting in more beautiful expressions. We do need debug. Never mind. Okay, so, oh, this is interesting. We have no par. Oh, I just created this. Oh, come on. Yeah, arg layouts. That's the interesting part. But yeah, hang on. I'm gonna clear my nose. Okay. Also closed the blinds and turned on the light because it was getting dark. That's winter, I guess. Okay, so yeah, this is the parameter layout for the closure, actually. I think. Yeah. Maybe let's see the arguments to this lambda from int to int. Okay. So it has many arguments. That's weird. Oh no. I think in the yogurt we already add some sort of closure. No, this seems almost fine. Maybe let's first fix the printing of lambdas or like of functions in the yogurt, and then yeah, the parameters get printed, and I also want to print the captured thing. So for each capture in hang on. This is not the right thing, but this one is. Yeah, we print the function key and then the function body. Yeah, but let's also print, like, you know, if function dot captures is some things that it captures, then we also want to print those. And that means, well, it's a bit more complicated. We print space and then something. And then in here we print the, like, for each capture thing in captures, we also print that. Something like this. Yeah, fun.captures is not something that exists apparently. Oh, because fun is a map entry, because this is a map that we're iterating over. Yeah. So now there will be some functions that, like most functions, don't capture anything, but this one lambda that we create that should capture something. Yeah, these don't capture anything, but the lambda, if we find that here, it captures 0 and 1, two variables that just, you know, from the surrounding scope, they should be available in here. So they are. And now we call that lambda. Okay, fair enough. And this is a lambda from int to int. So what we do essentially is we lay out the parameters of this lambda. And those are 3 parameters. That is strange. That's really strange. We have a lambda, archetypes. Oh, yeah, we have int and then the actual parameters and then int again. No, this first one was one too much. Okay, that makes sense. Oh damn. Okay, so something we get further in our compilation, I guess. And let's just look at the waffle. And in particular, yeah, this one, the lambda. Let's see. You know, let's maybe also go into the original source code, which means, yeah, let me open maybe a new window with syntax highlighting enabled. The plum extension, yes. Okay, so what do? We create a list 1, 2, 3, and then we pipe that into map with this lambda that first adds the item from the list to A, to the thing from the main function, sure, and then adds that to B, which is 4. Okay, so the closure of this lambda, it captures, item is an explicit parameter, but it captures A and B from the surrounding environment. So I assume that the closure must be something like, in the waffle, something like this. It captures 2 ints, and that should be allocated on the heap somewhere. And when you call this function, this lambda, actually when you create this lambda, that's actually just basically like a tuple, or like an aggregate, I guess, of a pointer to this thingy with the captured variables and the function pointer. And inside of the function, like when we call that function, we actually call it with the argument and that pointer to the captured variables. And the function, like the lambda inside, must take care of getting these captured variables from the heap. Okay, so what we do is we add the item that we were explicitly passed to the first captured variable. So we take this aggregate of all arguments, and at offset 0 size 8 there's the explicit argument, and the second one, oh look at this, these arguments at offset 8 there's size 8, there's a pointer to the captured variables. So we unbox that, we follow that pointer, and that should be 16 bytes because we captured 2 ints from the surrounding environment. And there at offset 0 size 8 should be the first int that we captured, like the A in our case. And yeah, we add those, and then we add the result of that, the 1, and yeah, we basically get the second captured thing, and that's basically the same as here, except that we have offset 8 instead of offset 0. Okay, that seems like this actually seems to be correct. That is crazy. And then so that's the first thing. Next, let's look at how that lambda is created. So in here, we create that list, and then we create a lambda. And that lambda is actually just a tuple of the captured of a pointer to the captured variables, so something boxed, a pointer to the heap. And on the heap, we will put the argument to the main function, and also the captured variable that is the int 4. So we will take those, put them in an aggregate, in a struct thingy, allocate memory for that on the heap, and that pointer, we will put that in here together with a function pointer to the lambda function that we saw above, this one. So this is 16 bytes, just a pointer to the closure and a pointer to the function, and that makes up the lambda. And then we just pass that to this map function. Oh yeah, and you can see that this list, which is 17 bytes, and then 7 bytes of padding, and then the actual lambda. Okay, that's the second place where lambdas are interesting, and now the third place, and that should be the map function. How are lambdas called? Here. So we do something. Okay, so we take the argument. That seems fair, yeah. And at offset 24, that is where the lambda is. We calculated that before. Size 16, because there's just 2 pointers. The second pointer is the function pointer, correct. So we dereferenced, this is like an indirect call basically. And the argument is this. It's the, what even is this? The explicit argument, from our arguments, this first thingy, so offset 0, size 17, the first part of that. So the int from the more variant. We pass that int along with the closure, hopefully. Yeah. So that would be 0.24, 16. That's the same thing as here, but offset 0 is the closure. Damn, that works. That is pretty amazing. That is super amazing. Okay. Crazy. So let's maybe look further. Did this actually work? I see down. Okay, so we have enough, space for the instructions. Damn, this is just nonsense to me, but sure. But then things don't work out exactly as we hope they would. Okay, so we call the list function apparently with 1, 2, 3, and then the list function does stuff. Calls the list constructor with only 2 elements. That calls the list constructor with 1 element. That calls, I don't know, some cast function probably, which switches on that thing. And yeah, it calls something else. Oh yeah, it casts the int probably. I don't know. Cast empty to empty or something. Okay, but then, we return from all that. We return from all that, and we return from all that. And then finally, we'll do something. Hang on. So there are all these things going on. This very much looks like, 17, size 17, skipping that is still returning from the list constructor. Pop below top, push something from the stack, call something. Oh, this does not look good. Definitely not. Okay, so I guess with the call thing, let's I don't even know like how do we make debugging this easier. Yeah, I guess first simplify the code. That's the first thing we can do. And here let's just return 0, and let's just create a lambda that captures one variable. And we don't do list maps and things with like switches and jumps and so on. But let's just create a lambda that captures a. Hang on. Okay. Yeah, simplify everything. So let's say this returns, just calculates a plus b, and then we return foo of 3. And I think we just hard code to call main with 5, so the result should be 8. Yeah. And that's like the first lesson I learned in compiler writing. Just simplify everything. Simplify everything as far as possible. Oh, expected body. Well, that's unfortunate. Maybe this might work. Okay, that does work. Interesting. So that is 3. Okay, maybe. I don't know. Oh. But not a lot of code that gets executed. That's cool. Okay, let's see if this contains all the essential stuff. Yeah, we take our argument, the int from that, and put that on the heap. And we also get a function pointer to the lambda. And then we create a 3, and then we call that function with the 3 and this one. Perfect. Yeah, okay, yeah, sure. And here's the lambda, where we call plus with the actual explicit argument is here, and this is the captured one. So taking the captured pointer, dereferencing that, containing an int, and then getting the int from that. Okay, so let's maybe look at the code. Oh, maybe I should. Yeah, I should probably. Should I? Yeah, let's look at the testing, like execution harness. Do we actually call that with 5? That would be kind of relevant to know. Bytecode.call. Oh, we call that with this crazy number, the hex number only consisting of 33 everywhere in hex notation. So this is really wrong, the result that we get. Okay, we can deal with that. How do we debug that? Let's maybe in the VM there were some commented out things. Yeah, let's print the VM. We run the instruction, and we also want to print the VM state. Between each instruction, and then we'll just see what happens. Okay. So much code for so little, stuff. Okay, so the main function gets called, and there's crazy numbers on the stack. Fair enough. Then we want to. Let's maybe see what's the first thing we do is we create a lambda, which is fair, I think. So to do that, we get that, push that on the stack again, push those 8 bytes. And then we push an 8. We want to allocate memory for the closure. Size should be 8, alignment should be 8. So we call malloc, which consumes the size and alignment and returns an address. Amazing. And now we want to copy that number that we want to capture to that position on the heap. So we push that address again. We push 0, offset 0 is where we want to save that. We add that, okay, add 0 to that, boom, we have our address. And then we push the data that we want to save there, here. And then we call store 8, and that just consumes the address and the data to save there. And yeah, those disappear. We're leaving us only with this. Yeah, we've saved a closure on the heap. Next, we pop something below the top. Oh yeah, there's temporary variable here. We no longer need that, sure. I mean, I guess. Next. Oh, this is interesting. We push some great constant, and that is probably the address of the bytecode function that we want to execute. Yeah. And then we push a 3 for some reason. Oh, okay, so this is our lambda actually, you know, a pointer to the closure as well as a function pointer. And then we want to call that lambda, so we push a 3. And no, calling means something else. Calling means that we now push the arguments. You know, first we create all the values, we've done that. Now we want to call that. So we push the arguments, aka the 3, and the closure pointer. The closure pointer, which means we push the entire closure consisting of the closure pointer as well as the function pointer. And then popping the function pointer again so that only the closure pointer remains. Definitely the most efficient way to do that. And then we push something else. Oh, now we push the function. Oh no, now we want to push the function pointer for the indirect call. So we push the entire closure again, including closure pointer, the entire lambda, including closure pointer and function pointer, and then popping the closure pointer, so we only have the function pointer in here. Oh man, and now we want to call indirect. And call indirect is going to pop that thing here. That's the function pointer. It's going to jump there. And yeah, below that are the arguments. So we called something, and now, boom, on the stack we have these arguments to the closure, to the lambda. The explicit argument of 3, as well as a pointer to the closure. So now inside the closure, what we do is what do we do in the closure? Let me maybe, we want to, okay, we just add that closure captured thingy and the explicit argument. Let's see. This is the closure. Okay, we want to push. We push the 3 for some reason. Okay. And we push the closure pointer. We push the entire arguments of the closure. Yeah, and then we pop the 3, so only the closure pointer remains. And then we push that again, yeah, push offset 0, sure, we add those. So now we've calculated the offset of the captured variable inside the closure, and we load that. So boom, we consume that pointer, and instead we replace that with what's stored there on the heap, aka our captured variable. And yeah, we pop the pointer below that, sure. So this is the first argument to our function. And then we also get the second argument, that's the 3. And now we actually want to call that function. So we duplicate those. Oh, hang on, we push something. This is the closure pointer again. Oh, and we reload that again. Maybe? No, we just pop that again. I don't know. Anyways, we call the closure. And we call the add function. Yeah. So we add 3, 3, 3, 3, boom, and just 3. And yeah, this is gonna take some time. So let's see, we have this call. I'm just gonna ignore all instructions except calls and returns. So we have another call. This is the built-in add function that's now running. It's gonna call the add instruction actually. Oh, and we have the sum here. Crazy. And then we return from the built-in add function with the result of that thing. And then we return from the add function. Boom, here we go. Crazy. And now we want to return from the closure. So we push the return value, boom. And we push we pop the local variables that we created in the process. Hang on, we push the return value, that's correct, yeah. We pop local variables, so we skip the the top 8 bytes and we pop the 8 bytes below that. Okay, yeah. And then we push, we pop the arguments, so we skip the first the 8 bytes that are the return value, and we pop 16 bytes below. Maybe that's correct. I don't remember what the stack depth was when we wanted to call the closure. Well, okay. So then we return from the closure. And I mean, at least we have the correct thing on the stack. So that's something. Oh, then run push from stack. Push 8 from stack. Why is that? Oh man. What's going on here? Push 8 from stack. It offset 8, but that's not the return value we want. I'm not sure. Then we pop all local variables below that. I mean, sure, yeah, that's. But why is this offset 8? Let's maybe look at the waffle of the main function. Yeah, here we call that function, and then we just return a result. Now, when we called that function initially, the call instruction, and we allocate the closure using malloc and stuff like that. Yeah, and we store stuff and so on. And then at some point we do call indirect. Okay, yeah, that, this is just the pointer. And then this is the stack here. And the function should consume these. And instead push the original value. So in the end there should be like 4 lines of something, and then this 3, 6, 3, 3, 3, 3, 3, 3. Let's see if that's the case. 4 lines of something, and then yeah, okay, that seems correct. All of that works. Why? What? Maybe call is not correct, like VM. In the VM it's probably correct, yeah, but in here, when we call something, yeah, we need to update things manually, sure. Oh, maybe call indirect is not. Hang on, we have padding in here. Okay, then we push the arguments to the call. Fair enough. We push more padding. Yeah, aligning the stack to 8 bytes, because then we want to push the function pointer. And we emit this call indirect, and that doesn't adjust the stack size, so that's something that we need to do. And after the call completes, basically, the stack size is going to be builder.stack size. So the current stack size. Minus stuff. Okay, so I think there's an 8 missing here. Because what's happening is, let's maybe put that in multiple lines as well. Let's maybe put that like this. Yeah. And sort these the correct way. So the call indirect instruction consumes function pointer. Yeah, the function consumes the padding as well as the arguments and pushes its result. Yeah, that's how it works. So maybe that's yes. Look at that. This is amazing. Okay, so lambdas just work. That is crazy. You know, that we just allocate memory for the captured variables, and then that is amazing. Damn. Whoa. Yeah, let's maybe, we had this print VM thingy. I'm not gonna do that. Wow. Okay, yeah, I think what's cool. I mean, the low-level stuff is working. Okay, let's maybe commit this first, and then there was one other thing I want to do before concluding this session. Oh, what do we even So many things changed here. Support lambdas. Sure. Tester plum. Yeah, I think that's sure. Support lambdas. Amazing. So one more thing regarding memory layouts. So earlier in this session I kind of struggled with choosing efficient layouts for aggregates. Let's maybe see what it does here. That was this part at the beginning. Yeah, choosing memory layouts. And basically, this is not great. Like sorting the fields first by decreasing size, then by decreasing alignment, and third by index. Let's maybe look at the, ignoring all this, just look at the memory layouting and exit after that. And run that, and we'll see that the memory layouting is not perfect, and not even great, Yeah. So what do we even do here? We have a layout consisting of some memory with size 3 alignment 2, then size 1 alignment 1, like a single byte, and then size 9 alignment 8. This could, for example, be a maybe int or something, which needs 8 bytes for the actual payload and then 1 byte for the tag, whether the payload even makes sense. And the way these are set up is, okay, this is actually efficient. But there are some examples where that doesn't work out as well. I'm not sure, maybe it's one of these. Let's see if this works. This is, hang on, 1 byte and an int. Yeah, okay, they make sense. First we put the int, and then the byte. Yeah, okay. How about this one? Does that work? What do we do here? We have something of size 3 alignment 2, then something of size 2 alignment 2, and size 3 alignment 1. Also optimal. Okay, but there are some... Okay, let me see if I can construct one. First we sort the fields by decreasing size. Yeah, that's already not great, because we could have something where we have something like this. A field of size 5. Or even worse, maybe. Yeah. Let's say we have a struct that contains a maybe int and an int. And the optimal way to lay them out would be to first put the int and then the maybe int, because then the entire thing will just be 17 bytes in size, 8 plus 9, and you don't need any padding for the fields to be aligned. Like offset 0 is divisible by 8, and offset 8 is also divisible by 8, fulfilling the alignment requirements of the fields. But what we actually do is we will sort the big fields first, so the field of size 9, aka field number 1, then have 7 bytes of padding, and then field number 0, so the total size will be 24. And this is, that's just stupid, That's really stupid. So I kind of struggled with this. I've looked at a lot of papers, how other languages do field reordering, and I think there was no great solution. So I asked some other people for help. Can I show that somehow? Ooh. So I asked a friend of mine, and he suggested to look at the poke a hole tool in Linux. Apparently, in C, like the C compiler doesn't reorder memory or like struct fields for you. You have to do that manually. The struct layout will just have the order that you provide. So there is an analysis tool that finds inefficient struct layouts. So it finds holes caused due to aligning the data elements. Yeah. Because again, like having fields in the struct doesn't just add to that, but actually, on a 64-bit machine, it's going to be like 40 bytes instead of 16. But by reordering the fields, things may get better. So there needs to be some sort of reordering algorithm in here, or like some, I don't even know what's in there, So there is this -- reorganize option apparently. To show the steps taken to compress the data. That's really interesting. PA hole, poke a hole, reorganize, and then you have some object file, and here is a struct. Oh, okay, so it basically moves the fields around somehow, it shuffles them, and then things work out better. Saved 16 bytes. Okay, hang on. That is like that. They're trying to solve the same or similar problem. Okay, the algorithm tries to compact the structure by moving the data elements from the end of the struct. Yeah, I mean that's more like for multi-core stuff. Yeah, sure. Okay, that sounds interesting. Hang on. Maybe look for PA hole Linux source code. I guess PA hole, something like that. Rules. I think this is out of date for. I mean that's. Oh, here's the link to a kernel thing. Oh god, I've never. Linux kernel thing tree sounds like it contains the files. Can we somehow search in this? Search. Reorder. Yeah, reorganize. Yeah, reorganize. Reorganize struct member. Oh, in the tool itself. Oh, that's pretty cool. Using the tool to improve the code that writes the tool. That And -- reorganize was it? Can maybe search for that directly, like --. Oh, but not log message, but yeah, we don't want to. We want to search in the tree basically. Okay, well, this seems correct. Let's just see how if that gets called. Oh, that's a big file. Reorganize, class reorganize, name reorganize. Oh, these are the parameters that you have. Yeah, the arguments that you can provide to the tool. Reorganize, do reorg, that sounds savings, okay. So it does class clone, and then class reorganize. And reorganizes that cloned class. And then prints that. Okay, so this is actually, yeah, this just, what is nice, it calculates the savings. So class reorganize. And class reorganize is, we can search for that here, probably. Maybe not. Is that in here? Yeah, this has class reorganize. Okay, try to combine wholes. Yeah, bit field stuff is not really important for us. Okay. It gets the last member. And then for each member gets the byte. Oh, the member contains the whole. Interesting. So rather than having a list of members and wholes, it's just a list of members, and each member has an actual size, and then the whole that's probably after the member. Oh. But I think that's too... What is it doing? We get some aligned size. See if we have a whole after this member. And then try to find a member that has a whole after it. Oh, and that has a size that fits the current whole. Okay, yeah. So for each field, each member in that type, it just looks at all the members afterwards. Like each member has a whole after it, and that may be 0, or if there is no padding afterwards, you know. But if there is a whole afterwards, then it looks for fields that come after that in the struct, and that fit into the whole. That is not enough to find an optimal layout, definitely. Yeah, okay, it does some bit field stuff that's not super interesting. Okay, sure, yeah. But anyways, like this doesn't find an optimal solution, you know. It just is a very simple algorithm of, hey, we have a struct with holes in it, let's see if any of the members in that struct fit into these holes. And if not, that's it. Like that, this is not, it's simple for sure, but not optimal. So yeah, I also asked on Reddit and the programming languages Discord, where I basically said that, hey, I want to store a set of fields, and each field has a size and an alignment. Yeah, blah, 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 like the size is not required to be a multiple of the alignment. And then, you know, I looked at other languages and I basically described what I found. Like C doesn't reorder fields, so the layout is not optimal. Rust requires sizes to be a multiple of the alignment. So if you have nested structs, that's not optimal. You know, Zig is just focused on getting a self-hosted compiler running, and Zig is still very, very early in its implementation, and there are a lot of more important work to do than optimizing struct layouts. So they just use the C layout for now, and also fair. LLVM couldn't find anything. Haskell just uses pointers everywhere, basically. Yeah, painters literally sorry. Many papers focus on more crazy optimizations like struct splitting and array of struct to struct of array conversions. That's basically what I found out. And yeah, I just asked people, how do they deal with that? Do they deal with that? And yeah, so one option was, you know, sort by decreasing alignment, and that's basically what, no, we sort by decreasing size. But when you're having some simple heuristic, currently is, oh, that's actually wrong. Currently I sort by decreasing size, but yeah, having some simple heuristic, and then that should be fine, you know, that's sure. Brute forcing is exactly what I did in Martinaise. I probably showed that already on this in the session. Yeah, putting it in a solver like that's no. Right. What was this? Oh, this was really interesting. You know, data-oriented design. So basically, rather than having structs, you just store well, you basically store separate arrays for every kind of type. So if you have a struct, for example, all of the fields will actually have different arrays. And all the, I don't know, foos that exist in your program, there will be in this kind of foo field, you know, there will be an array of all foos that exist in your program. And there will just be an index in that list, basically. And when you access foo.something, you will actually look in the correct array for that. That is interesting, like really, really interesting, actually. And it is something that, yeah, if a method only uses some of the fields, for example, if you have some sort of game and you calculate the offsets of objects, or like the positions, you know, you want to do some physics stuff, then the way to do that is by you only need some of the fields. You don't need all of the like special sound effects and items that a player has or something. Like the only thing we're interested in for every game entity is just the x and y coordinate, and maybe like a velocity or something. But basically you have this few arrays that only contain the necessary information, so it's super efficient because it doesn't need to load all the health information and items and so on. But all this position information of all entities is packed together somewhere. So that is really interesting. Yeah, I know there was some like experimental JavaScript engines in development, like not V8, but some other more niche engines that also try to use data-oriented design by having these arrays for every, like just creating a new object in JavaScript would basically create these new arrays, and if you have multiple objects of the same type, I'm gonna say, or the same shape, they're actually gonna be stored in the same array, and you have your different arrays for each field. This is a pretty like modern solution. Yeah, really interesting. It's probably too much to do right now. Like this is not something. This will take a lot of time, like building this out, and it's not even sure if this is viable, if this is something that improves performance, or if it just makes things more difficult for the sake of it. Yeah, and I like that currently memory is all local, that you don't have this global reasoning, this global list of objects, for example, or this global anything. There was no global garbage collector even. But instead, this language is, you just have memory fragments, and sure, if you have data, then you just have memory, the data is just all over memory, but each data is located like it is in the code. And I think that's maybe not an optimal solution, but at least it's something that is easy to reason about, and it makes it easy for Plum to interoperate with other languages, with a host language basically. Currently Martinaise, but if you at some point, like if you want to write an interpreter in Zig or C or Rust or something, you basically have this stack, and when the program finishes running, then you just have a normal value somewhere in memory that is really easy to interpret, rather than having these global structures. And I want my language to kind of integrate well with these existing languages. And that means that I don't want to adapt an entirely new philosophy of organizing data. At least for now, that's like super, super advanced and super... It is probably doable if I put a lot of time in there, but it's not what I want to focus on. And that's the entire idea. Okay. Yeah, letting the user pad things is necessary. So the thing that makes this difficult is that my language has a structural type system. So for example, these types should be compatible. So they should have the same memory layout, and that means the compiler needs to choose a memory layout. You can't just require the user to explicitly add padding in there. Yeah. So the next thing was, like just not care about alignment. That's definitely a way to do that. Blah, 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 blah. Oh yeah, here I had some examples for why the strategies are not optimal. If we sort by decreasing size, which is essentially what we're doing right now, then this fails. In our case, we had a field with size 9 and a field with size 8, and here size 9 and size 8, and that order is not optimal. Like you want this order rather than this order, what the compiler chooses right now. So yeah, decreasing size fails for these kinds of fields, where multiple fields have the same alignment, but one is maybe wrapped in a maybe or some other enum, so it has some extra tags on the end. And yeah, you will sort those first and have some really nasty padding in between. That's bad. increasing size is also not not better, because you might have some fields that are like very big, because this is maybe a struct with 2 ints inside. And then these weirdly sized enums will still be put at the beginning. Bad. Next, decreasing alignment. Fails for some cases, increasing alignment as well. I'm not gonna go into too much details there. Okay, I packed things, I care about alignment. Yeah. Bin packing. Bin packing. What is bin packing? Bin packing problem. An optimization problem. Different sizes must be packed into a finite number of bins or containers. Yeah, okay, the problem is NP hard. I'm not sure if that's... Items of different sizes, yeah, must be packed into a finite number of bins or containers. Okay, yeah, no, that's not exactly... No, that's not really the problem. Yeah, okay. Yeah, so there are some optimization or like heuristic algorithms, you know. Okay, yeah, not really what I'm trying to do. So, I did have an idea though. Let me maybe show that on my iPad. Yeah, maybe I'm not gonna draw anything after all because my battery is empty. And also I think this is fine to demonstrate in here. So I was thinking, let's maybe go back to these examples where things don't work out with these simple algorithms. They all fail because they put these weirdly sized structs in the beginning. Like size 3, this gets put before this nice roundly sized struct. And similarly here, and here, and here. So I was thinking, what if we order fields based on how roundly sized, how nice and evenly sized maybe they are. So that's something I want to at least think about. So I'm maybe going to copy these and just do some thinking in here if my iPad is not working. Yeah, let's maybe put that in a comment and then we can work on that. So the idea is basically this. Sort first, like basically group fields into buckets, you know. First, fields where the size is a multiple of 8. Then fields where the size is a multiple of 4. Then fields where the size is a multiple of 2, and then, all other fields basically. And I think that is actually what you want. Even in the Martinaise compiler, in my previous language, hang on, I have a link somewhere here to the exact part of the code. Yeah, here I calculate the memory layout. Yeah, basically I find out the alignment of all the fields, and then I do this. Fields with a size that's a multiple of the alignment can all be put at the beginning. And yeah, this is the cursed option of trying all permutations of other fields, limited to 1,000 permutations to find minimal layouts. But you know, this idea of putting these roundly sized fields first is something that's, I think that should work out. It's not optimal in all cases. You know, like you can have weirdly shaped fields, like, I don't know, some field size 3 alignment 1 and one field size 5 alignment 1. And really you want these to, like, you may want to put these in at the beginning of your struct, because then they are aligned to 8 bytes, you know. Like, okay, sometimes you need stuff like this, but yeah, what I want to say is that this algorithm down here of placing fields in this order is not optimal, but that's fine, because for the vast majority of fields, I think, this is going to work out pretty great. Like, at least, you know, for the you won't have any blunders like here. If you only have 2 fields, by the way, I think this is always optimal. Not entirely sure, but I think it is. Okay, maybe not. Yeah, maybe not. But still, I think in the vast majority of cases, it's going to work out. Yeah. Yeah. Also because I think that fields where the size is a multiple of 1 or like of 2, the smaller sizes, this will be more like either something like a maybe int, you know, something very big and weirdly sized that you want to push at the end of the struct, or it's going to be something that is really small, like a single byte, or like 2 or 3 bytes, you know, like a bool maybe, or some other enum. And those can like neatly fit into the holes that your previous fields left. So I think in this algorithm, these really small fields, they don't have an alignment requirement that's big. These really small fields, they have low alignment requirements, so they get sorted last. But at the same time, these weirdly sized fields also get sorted last. I think that's a nice trade-off, and I think in practice that's going to work out great. So let's maybe just implement that. I think there's a better like baseline layout than what we do currently. Yeah, layout aggregate is where we do that. And yeah, group fields, like place in this order. Fields where the size is a multiple of 8. I don't know, by decreasing size, I guess. Yeah, place the fields in this order. Just by the evenness or roundness of the field's size. Second, in decreasing alignment. Sure. something like this, I think. The index doesn't make any sense. I think, okay, yeah, maybe not even this. Yeah, let's maybe remove this, and second by decreasing size. Okay, so yeah, first we sort all the very even fields, and then the smaller and weirdly shaped fields. And if there are some holes in the beginning, then we want to first fill them with fields that are like, you know, fields that with bigger fields. Yeah. We don't want to fill some big hole with a couple of small fields, but we first want to check the bigger fields. Like, put a big field into that big hole, and then those other small holes, they can be filled with the smaller fields. So yeah, we want to give big fields the priority. So that's why that is there. Yeah, let's just see how this works out. So we have a field memory layout, which has a size and an alignment and an index. Okay, and then we sort them. And up here is where we do that. Oh man, yeah. So second, by decreasing size. Yeah, the alignment doesn't really matter at all, actually. That's interesting. Yeah. And size is weird, you know. Evenness of some layout. At least that's what it's called down here, you know. So if layout.size is a multiple of 8, yeah, that's basically it. And then we do that same thing for 4 and 2, and otherwise we return 1 by default. Yeah. And here we just choose the evenness as the thing to worry about. And now this should actually be efficient, hopefully. Instead of like at least more efficient than this. Field 1, then padding 7, and then field 0. Let's see if that works out. Oh yes, it does. Oh yes, no longer size 24. No, now we have size 70. Okay. So I guess memory layering just works. That is crazy. I think that actually concludes like the low-level parts of the system. You know, like in the beginning I spent a lot of time working on the bacon and then the toast and the egg, the yogurt, and then I just had this object-based bytecode. And I iterated over this top part, you know, fleshing out the language, making the language more powerful. And then I was in the mood for some low-level stuff and basically replaced the backend with some memory-based, byte-based bytecode, which is a lot more low-level. And we have to decide on memory layouts for objects, for values, and stuff like that. But now I think the backend here is basically complete. So I think in the next sessions we'll actually look at these top level things and work on the language, you know, adding new features, new stuff to that. rather than digging around in the low-level details. Okay. Yeah, let me maybe push that thing as, I don't know, improve memory layouts. Improve memory layouts, yeah. And there were some other things like, yeah, in the waffle, I think. Up here, this is not how it looks currently. So, yeah, creating and accessing a struct is this. Oh yeah, and this is instead this. Yeah, and this is just 0, 1, and byte is just 1, and word is 8, and padding should all. Do we format padding like that? Oh no, I think we should actually do that. Yeah. Then the size is always, you know, written as a colon thing. Makes sense. We can even write the size in here maybe. Yeah, let's do that. I like that. Like this. With a space in here? I don't know. Oh, it's probably fine, like this. Yeah. Yeah. Oh, this is amazing. So you have this lambda of size 16, you have this of size something. That's great. Yeah. Oh yeah, here as well. 0 contains args. So that's maybe, oh yeah, ID index. Ooh. Contains args. Ooh, can we get, oh yeah, fun is fun.value.get 0, I guess. I'll get waffle ID with index 0 dot size, something like that. Index is not, yeah. Basically printing the size of the argument aggregate. Like this, yeah. So you can see that add actually takes an argument aggregate of size 16. Yeah, that's pretty amazing. Okay, so there are some debug thingies still. That was in Yogurt 2 waffle, I think. Yeah, the arc layout. No, don't want that. This one probably don't want that. Waffling something, maybe. I don't know, maybe. Yeah, this one definitely not. Okay, also I want to print a more, like, you know, work on try the more complicated example of creating a list and then mapping that, because that would be pretty amazing. So list 1 to 3. Or let's maybe write a simple sum function and see if that works. Oh man. So that's gonna be up here. Sum of a list, which for now is just gonna be a list of ints, and this is gonna return an int. And this is gonna return, well, actually it's gonna switch on the list. Yeah, if it's empty, then it's gonna return 0. If it's more, then it's gonna return plus of the item and the sum of the rest of the list. Amazing. Yeah, 1, 2, 3, and the sum of that is 6. Yeah, now let's try to map that list using some closure like this. Yeah, I guess b equals 1. Then we just get the item plus b, sure. If this works, then that's great. It's gonna be 9, right? Sad. Like that. Oh no. Yeah, lambdas have to be on a single line for now, because that's just the way it is. Should add single line lambdas. That would be useful. Okay, so something is not working. That's I guess in the lambda. Okay, so yogurt ID 0 is not in the map. Yogurt ID 0 is not in the map. Hang on. Where's the lambda? In here, lambda captures 1. That is strange. Oh, yeah, I think, in the main function that has the ID 1. Yeah, and this is correct, like this captures 1, but the lambda itself should, from the point of view of the lambda, this should be ID 0. So, where's that? That is in something to yogurt, in empty yogurt. So if there's a lambda, if the captured aggregates, the captured variables, and then in here, within the lambda, those should not be that should actually work. Hang on. Why doesn't that work? Some captures is what it says down. Oh, but that's those. Okay, so the surrounding function creates. No, hang on. Yeah, that's in here. Like the surrounding function creates a lambda with captures. That's fine. Like that's totally what we want to happen. But inside the lambda, this yogurt fun should actually capture the inner variables, basically. These kind of similar to the parameters here. Like in this function, yeah. The parameters become the parameters here. And similarly, we want the captured variables. Is captures used anywhere else here? I don't think so. Because like inner captures, I guess. Captured values from the point of view of the function of the lambda. Yeah, and similar to how we add the parameters here, we do that same thing with the captured inner captures. And then inner captures is down here. Yeah, here we can basically do that. Yogurt fun. Try to assign map, maybe from list yogurt ID to field captures. Oh yeah, because yeah, let's convert that to a slice. Of course. It just works. It just works. Amazing. That is crazy. That is honestly crazy. What? Take a list, then we create a lambda consisting of a closure on the heap and the function pointer, and then we map that, and then we sum that. What? That is. So I take a list of 1, 2, 3, map that to 2, 3, 4. 2, 3, 4 is sum is 9. Yeah, that is crazy. Okay, yeah, I guess the low level part officially works. That's pretty nice. Yeah, let's maybe actually clean up the output of. Oh, hang on. Let's push this first, because this is a very important bug fix. Let's see. This is just print improvement. Yeah, fix. Yeah, let's actually look at the yogurt before committing that. The map function. Oh no, the lambda is what I want to look at. Yeah, okay, so the lambda captures 0. Yeah, that calls that. Okay, that seems fine. Okay. Yeah, fix lambdas. Boom. Yeah, improve printing is gonna be the next commit, I guess. But I just wanna actually improve that a bit more. By not printing so much stuff. Yeah. And not printing the yogurt and waffle every time, and the toast, and the echoes never print. Interesting. All the waffling and compiling and there's just a lot of stuff going on, you know, compiling call, like that's ugh. Compiling call, yeah, no, just no. Compiling map, compiling signature. I don't know about that. I'm probably gonna keep that in here for now. We need a cast. Yeah, I'm gonna leave all of that in here, and hang on, the waffling maybe not. probably gonna be like this. Can I put that on a single line, maybe? Ooh, barely. Okay. Yeah, I'm still gonna print a lot of stuff, but yeah, I guess. We're collecting captured variables. And there was all this stuff. What is that? Toast? The bacon? The egg. Oh, I do print the egg. I see. Yeah, like manually creating a waffle, I'm just gonna remove that, as well as these memory layout experiments, you know? Just trimming this down a lot. Yeah. Yeah, no universe, Big Bang thing. Yeah, this is a lot cleaner, I think. Okay, yeah, like this is actually readable, relatively readable. Okay, collecting captured variables. No. Okay, so welcome to the Plum compiler, and then just compiling, boom, adding runtime cost. Okay, whoa, it fits on a single page in here. Yeah. Gonna clear my nose. Okay. Yeah. This is, you know, we could remove this. Yeah, I mean, okay, I'm basically finished with the low-level part of the compiler. Like all this part. I mean, I guess next would just be, I have some ideas on how to refactor the comp time stuff. So, you know, how to maybe present what kind of things are comp time evaluated while compiling the function, and clean up the code in that regard, because like this language is not, this is very evolutionary, this development, you know. The language in the first session I created was totally different than this one. Like, I didn't realize that I needed recursive types, and I thought that, hey, all types are inferred, and I think this session was a lot of struggling and figuring things out, and like, I don't know how to create optimal memory layouts, and how to a lot of this development is just figuring stuff out, and I think now the cornerstones of the language have somewhat settled. There is a relatively robust backend for the language, this VM, and I think it has nice abstractions for, like, this is something that is low level enough that you can easily write interpreters for that in Rust or Zig or some other low level language. So I think that's a very nice baseline, a nice compilation target for this language. And the things that are built on that, like the waffle and so on, I think they are also quite clean semantically. It took a lot of time to figure that out, you know, to figure out, like, how do I organize the waffle? How do I do that? Like, how do I even... It took some time for me to just realize that I need some intermediate stage between the yogurt and the bytecode, because the abstraction gap was so huge, and the waffle slots right in there. And still, a lot of things there are not directly working, like reference counting, for example. We just kicked that out when we switched to an interpreter. So I will have to figure out how to integrate reference counting into the waffle. That's something that's not done currently. There's not even a free instruction. But yeah, I think in general things are kind of working out, and that's pretty amazing. Yeah, cool. I'm just wondering, is there something else? I think next session, like I said, I'm gonna focus more on the language itself again. And we basically finished this detour into the low-level workings of, let's build a bytecode-based, stack-based VM, and now I can focus on high-level stuff a bit more, on like comp time stuff, and things there. Yeah. So I guess that's it for this session, and see you then.